Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. The sun rises in silence, but its presence is a chorus that has echoed through every age of life on Earth. Every morning, its gentle light spills over the horizon and washes the world in gold. In that light lies an ancient promise: warmth to nourish the living, energy to spark the green fuse of plants, and comfort to chase away the chill of night. For as long as creatures have walked under the sky, they have felt the sun's touch and known instinctively that this brilliant star is the giver of life. Yet the sun is more than a kindly nurturer. It is a colossal power, a raging sphere of fire suspended in the darkness of space. From across the cosmic void, it seems tame, a perfect golden disk that rises and sets with reliable grace. But up close, it is wild and untamable, a seething ocean of plasma and magnetic fury. It holds Earth in its grasp, guiding the dance of days and seasons, and it could, in an instant of cosmic anger, scorch our world lifeless. The same sun that gently warms our faces can also unleash deadly radiation and storms of charged particles. It is a giver of life, and it can be a destroyer of worlds. Our ancestors revered the sun as divine, calling it by many names and worshipping its life-giving light. They built great stone circles and temples aligned to its rising, celebrated when it climbed high in summer, and feared its waning in winter. In rare moments, when the sun vanished in a daytime eclipse, they watched in dread and awe as day turned to twilight, praying for the light to return. They sensed its dual nature, its generosity and its danger, even without knowing the science. We now understand that the sun is a star, one among countless others in the galaxy. But to us, it is unique. It is our star, the hearth of our solar system, the steady heartbeat of our cosmic home. It beats silently, a deep thrum of nuclear fires and magnetic pulses that we cannot hear, but that sustains us nonetheless. Every ray of sunlight is a note in that silent symphony, a connection between our small lives and the vastness of the cosmos. Consider this: the light that caresses your skin today began its journey at the core of the sun long before you were born. The warmth on your face is the end of a story that started deep in a stellar furnace. The sun bridges our brief human moment and deep cosmic time. It links the atoms in our bodies to the atoms in distant stars. In its light, we find both our origin and our destiny. We stand in the glow of a cosmic engine, often unaware that above us, a star's turbulent heart is burning and beating ceaselessly. To truly know the sun, we must journey into its very heart. Let us leave behind the blue of our sky and travel inward into the blinding brilliance, into the inner sanctum of our nearest star. What we find there is both humbling and wondrous, a story of creation and destruction, of light and darkness, of a star's life from birth to death. It is, in many ways, the story of ourselves, written in the language of light. Imagine plunging through the sun's surface and journeying toward its center. As we descend, the light intensifies and the heat becomes unimaginable. Deep inside, at the very core of the sun, we enter a realm of staggering pressure and temperature. Here in this stellar heart, hydrogen atoms are crushed together so tightly that they fuse into helium. In that act of fusion, a tiny bit of matter transforms into pure energy, an alchemy that powers the sun. This is the engine of creation hidden in the sun's core. Every second, an immense burst of energy is released, radiating outward to keep the star shining. Gravity presses inward relentlessly, trying to collapse the sun under its own weight, but the fury of nuclear fusion pushes outward, holding the star up. In this balance between gravity and fire, the sun's core burns steadily, a sphere of blazing plasma denser than solid iron and far hotter than any furnace on Earth. The core is a place of extremes beyond our experience. Its light is born in blinding abundance, yet none of that brilliance escapes directly. Only ghostly particles called neutrinos slip away unhindered, streaming out from the core and passing through the sun's layers, and even through our bodies on Earth, as though nothing were there at all. They are the silent heralds of the sun's heart, whispering of the nuclear fires within. Moving outward from the core, we enter the radiative zone, a vast internal layer where the energy from the core migrates slowly outward in the form of light. Here, photons of radiation ricochet through a dense maze of atoms. A single particle of light, born in the core's fury, may bounce countless times from one atom to another, absorbed and re-emitted in an endless random walk. The plasma in this zone is so opaque and crowded that progress for any ray of light is agonizingly slow. Ages pass as the energy inches its way outward. What we eventually perceive as sunlight on Earth has spent eons fighting its way through this hot, stifling labyrinth. In these deep regions of the sun, energy is transferred not in a simple beam, but like a traveler lost in a thick forest, zigzagging gradually toward freedom. Eventually, the character of the sun's interior changes. Further out, the stellar plasma becomes cooler and less dense, and it can no longer transport energy purely by the random diffusion of photons. At this point, a new process takes over: convection. We have entered the convective zone, the sun's outermost interior layer, where heat is carried upward by the motion of the gas itself. Picture an immense cosmic cauldron boiling slowly. Hot plasma from the layers below becomes buoyant and rises toward the surface, carrying energy with it. Upon reaching higher, cooler regions, it loses heat, becomes denser, and sinks down again to be reheated. These rolling currents form giant looping cells of plasma the size of continents, rising and falling in rhythmic surges. Through the convective zone, energy that once took millennia to crawl outward now surges toward the surface in a matter of mere weeks, riding the updrafts of this titanic, boiling motion. At last, the energy reaches the visible surface of the sun, the photosphere. This is the layer where the sun's light finally escapes into space and shines freely across the solar system. To our eyes, the photosphere is the sun's radiant face, a glowing golden disk with a sharply defined edge. Up close, it would not appear smooth at all, but finely textured and ever-changing. The surface seethes with the imprint of the convection below, a pattern of granules, like a vast mosaic of luminous cells. Each granule is the top of a convective plume, a cell of hot plasma rising from the depths. Their centers glow bright and white-hot, where fresh energy wells up, and their edges darken to a deeper amber, where cooler plasma is sinking back down. This granular pattern continually shifts and reforms, as though the sun's face is a living, boiling sea of light. Here and there, the photosphere is marred by dark blemishes, sunspots. These spots are cooler than their surroundings, and so they appear nearly black against the brilliance of the sun's face. A sunspot is born from the sun's magnetic mischief. Intense magnetic fields well up from inside the sun and suppress the hot rising gas, creating a region that is slightly less hot and thus darker. Sunspots can grow to be larger than the entire Earth and may last for days or weeks before dissipating. They are a sign that the sun's magnetism, though invisible, is ever present, knitting itself into the solar surface. We will soon see how these magnetic forces can erupt in violence, but for now, standing at the surface of the sun, we behold a roiling ocean of fire extending in all directions, a vista of constant boiling creation. Peering at the sun's face with sensitive instruments, we find that it is also vibrating subtly. The boiling convection within causes the sun to ring like a resonant bell, Its surface shivers in patterns, waves traveling across and through the sun, making the whole star gently pulse. Astronomers use these pulsations, this music of the sun, to probe its interior, much as one might learn the shape of a bell from the sound it makes. Through this solar symphony, we can discern the flowing currents deep inside, the building magnetic fields, and even hints of the sun's core, all hidden beneath the blinding glare. Rising above the photosphere, the sun's atmosphere continues outward in layers of increasing mystery. Just above the visible surface lies the chromosphere, a tenuous veil of gas that appears as a faint, pinkish glow. Here, the temperature, which had cooled at the photosphere, begins to climb once more. The chromosphere is like the sun's shimmering halo, visible clearly only when the bright photosphere is hidden during a solar eclipse. In those rare moments, it can be seen as a thin rim of ruby light encircling the moon's silhouette. Within the chromosphere, slender jets of plasma, called spicules, continually shoot upward, each one ephemeral and short-lived, lasting only minutes before falling back. The chromosphere is a restless transitional zone, a place where the fury from below meets the stillness of space above, and the solar atmosphere prepares for an abrupt and profound change. Above the chromosphere lies the sun's crown, the corona. Faint and otherworldly, the corona is a vast halo of pearly light that surrounds the sun and stretches far into space. It is breathtakingly beautiful and enigmatic, revealed to human eyes only during a total solar eclipse, or through specialized telescopes that block the sun's glare. In those brief eclipse moments, when daytime twilight descends and the moon hides the sun's brilliance, the corona appears as a pale, white aura, etched with luminous streamers and delicate filaments extending in all directions. But the corona is not merely a spectacle of light, it is a furnace in its own right, one far hotter than the sun's surface below. While the sun's photosphere is blisteringly hot, the corona above is unimaginably hotter, a puzzling reversal of what one might intuitively expect. In this outermost layer, the sun's magnetic field rules supreme, shaping the thin gases into graceful loops and arching structures. Great magnetic arches rise high above the sun, filled with incandescent plasma that traces the invisible lines of force. The corona is incredibly thin, its particles so sparse that if you were standing in it, shielded somehow from the heat, you might not even notice the few atoms brushing by. And yet, despite its tenuousness, the corona possesses immense energy and reaches temperatures of such magnitude that scientific instruments must strain to record them. Why does the corona burn so fiercely? It remains one of the sun's lingering mysteries. Perhaps the sun's tangled magnetic fields thrash and snap, heating the gas in a myriad of tiny explosions, or waves of energy ripple outward from the sun's surface, dumping heat into the corona. Whatever the cause, the sun's crown glows with an ethereal fire that science is still striving to fully understand, a reminder that even our well-known star holds secrets at its heights. At the edge of the corona, the sun begins to fade into the darkness of space. There is no sharp boundary where the star ends. Its atmosphere simply thins into the void. Here, the corona gives birth to the solar wind, a ceaseless stream of charged particles, electrons and protons, that flows outward in all directions. The sun, in effect, is always breathing out. Its breath is the solar wind, and it carries a piece of the sun's essence out to the farthest planets and beyond. The gravity that so overwhelmingly confines the core cannot hold these fast, lightweight particles of the corona. They race outward along open magnetic lines, escaping the sun's grip. The solar wind is, in a sense, the sun's extended atmosphere flowing freely into space, filling the solar system like an invisible, ever-expanding bubble. We have now traveled from the sun's core, where matter becomes energy, to the wispy fringes of its corona, where the star dissolves into the broader cosmos. In this journey, we have witnessed the anatomy of a star, its layered realms, each with its own wonders. We have seen the ferocious furnace at its center, the slow upward struggle of light, the boiling convection that brings energy to the surface, the radiant face shining into space, and the crown of fire that reaches beyond the sun itself. Yet the sun is far from a static ball of gas. It is dynamic and alive, its surfaces and atmosphere writhing with magnetic fields and sudden eruptions. To truly understand our star, we must explore these invisible forces that bind and sometimes unravel the sun's material. We must watch as the sun's calm radiance is punctuated by storms, blazing flares, erupting prominences, and billowing clouds of plasma that can span millions of miles. It is time to examine the sun's magnetic heart and the space weather it breathes into the solar system. Beneath the sun's bright face lies an unseen web of forces that drives its most dramatic behavior. The sun is a giant magnetic dynamo. As it spins on its axis and its plasma churns, it generates magnetic fields that thread through its interior and arch out into space. Imagine lines of unseen force looping out from the sun's depths, arcing high above the surface and diving back down. These magnetic field lines become twisted and tangled by the sun's constant turning and boiling. Where they burst through the surface, they drag up or suppress hot plasma, creating the dark sunspots we see freckling the photosphere. Every feature we observe on the sun, its spots, its flares, its glowing coronal loops, is shaped by magnetism. Without the magnetic field's influence, the sun would be a far more monotonous star. Instead, magnetism makes it a living, breathing, and sometimes tempestuous entity. Sunspots are the most visible signs of the sun's magnetic moods. They tend to appear in groups, often as pairs linked by a great looping magnetic field. One spot will have a north magnetic polarity, the other a south, like opposite poles of a bar magnet. The arc of magnetism connecting them traps cooler plasma in its grip, outlining structures we sometimes see as prominences, towering loops of glowing gas that stand above the sun's surface. Sunspots grow and shrink as the magnetic fields beneath them strengthen or decay. Over days or weeks, a complex sunspot group may evolve. An enormous energy builds up in its tangled magnetic knots. There is a rhythm to these appearances. Roughly every decade or so, the sun swings from a time of few sunspots to a time of many, and back again. At the peak of this cycle, dozens of spots can dance on the sun's face. At the low point, the sun's visage is often clear and quiet. Each cycle, the sun's magnetic poles even flip. North becomes south, and south becomes north, as part of this regular heartbeat of our star. Our sun, like a living thing, has its seasons of storm and calm. When the stress in twisted magnetic field lines becomes too great, they can suddenly snap into a new shape, much like a tensed rope that finally breaks free. In that instant, the energy that was bottled up in the field is explosively released. This is a solar flare. On the sun's surface, a flare is a blinding flash of brightness, a sudden blaze of radiation across the spectrum. It is as if a patch of the sun's surface has detonated with the power of countless nuclear bombs. In minutes, a flare unleashes a torrent of X-rays and charged particles into space. If the Earth lies in its path, these emissions race toward us at light speed, arriving just minutes after the flare erupts. Our planet's upper atmosphere suddenly swells with energy. Radio communications can crackle and fade as the ionosphere, the atmosphere's charged upper layer, is pummeled by the onslaught, and astronauts in orbit might hastily seek shelter from a burst of radiation that moments before was not even known to exist. Flares are often accompanied by an even more massive eruption, the coronal mass ejection, or CME. Where a flare is a flash of light and high-speed particles, a CME is a giant cloud of solar plasma hurled out from the sun. When a particularly complex magnetic loop in the corona destabilizes, it can fling away a chunk of the sun's outer atmosphere entirely. Imagine a colossal bubble of electrified gas, more massive than all of Earth's oceans combined. suddenly launched into space and expanding as it races outward. A coronal mass ejection can contain an astonishing amount of matter and energy, an immense, billowing storm front in the emptiness of space. If one of these solar tsunamis is aimed toward Earth, we will know it soon enough. Within a day or two of the eruption, the wave of solar particles reaches our planet. Earth's magnetic field recoils and reverberates from the impact, like a bell struck by a hammer. We call this disturbance a geomagnetic storm. When a geomagnetic storm engulfs Earth, the results can be both beautiful and dangerous. Under the night skies at high latitudes, ghostly lights burst forth. Auroras, the northern and southern lights. Normally, auroras are confined to the polar regions, tracing the shape of Earth's magnetic field as it directs the sun's particles toward the poles. But during a strong solar storm, auroras can be seen much farther from their usual homes, painting the skies in eerie greens, purples, and reds over a vast swath of the world. Imagine waking in the tropics to find the night sky alive with rippling curtains of light. Such an astonishing sight has indeed occurred when the sun lets loose one of its great storms. In ages past, people who witnessed auroras far from the poles were often terrified. They saw in them dragons or celestial armies, believing the heavens were aflame with omens. To ancient peoples, these luminous dances in the sky must have been both wondrous and terrifying. Even today, knowing their true cause, one cannot watch the aurora's shimmering display without a feeling of reverence for the forces at play. Yet along with this beauty comes disruption. The same geomagnetic tempest that sets the skies aglow can wreak havoc on our modern technology. The barrage of charged particles and the distortion of Earth's magnetic field can induce surges of electric current in long conductors here on the ground. In our age of wires and wireless signals, a strong solar outburst can interfere with radio transmissions, scramble GPS navigation, damage satellite electronics, and even overload power grids, plunging cities into darkness. Over a century ago, a monumental solar storm made telegraph lines spark and catch fire. Telegraph operators found they could disconnect their batteries and still send messages. So powerful were the electrical currents coursing through the wires. If a storm of that magnitude struck today, satellites might be knocked offline, and extensive blackouts could occur. For all our technological might, we remain passengers in the sun's domain, subject to its occasional fits of violence. This turbulent interplay of solar magnetism and its effects on Earth and the planets is what we call space weather. Like weather in Earth's atmosphere, it has calm days and tempestuous days. The sun's magnetic field is ever shifting, and as it does, it breathes out gusts and squalls into the solar system. Most of the time, the solar wind blowing past Earth is a gentle breeze, and our planet's magnetic field shrugs it off with little fanfare. But when the sun erupts, the space around Earth becomes a stormy sea. A surge of charged particles and magnetic disturbances crashes against our planet's defenses, and near-Earth space itself reacts in kind. Auroras lighting up, satellites feeling the shock, currents coursing through the ground below, where all seems quiet. Fortunately, Earth has a sturdy shield. Our planet's magnetic field envelops us, carving out a protective bubble that the solar wind must flow around. This magnetosphere diverts most of the charged solar particles, allowing only a portion to funnel down toward the poles. In the clash of sun and Earth, the auroras are the glowing traces of our magnetic shield intercepting the solar storm, a testament to the protection it offers. Planets without a significant magnetic field, like Mars, have no such guard. Over eons, the sun's relentless particles stripped away much of Mars's atmosphere, leaving it a cold, arid world. In that fate, we see mirrored the dual nature of our sun, the gentle provider that sustained life on Earth, and the relentless force that can erode a planet's very sky. It nourished Earth with light and warmth, while its winds slowly wore Mars down. Magnetism is the hidden architect of the sun's behavior, from the steady cycle of sunspots to the wild drama of flares and auroras. Through it all, the sun continues to shine steadily in our sky, a reassuring beacon of day. But we have learned that beneath that steadiness is a flickering heart of magnetic energy. The sun's calm and its storms are two sides of the same coin, both born from the same stellar heartbeat. As humanity extends its reach into space and relies ever more on technology, studying and forecasting this space, weather becomes increasingly important. We now watch the sun with eyes open, tracing its spots and flares, listening for the whispers of its solar wind. We have even sent spacecraft to touch the sun's fringes, sampling its corona and feeling its magnetic embrace, all to better understand our star's moods. In the midst of these stellar tempests, it is easy to lose sight of the sun's most gentle and steadfast gift, the sunlight itself. Every day, countless photons leave the sun and stream across space, and some of those reach our world to illuminate the sky. Consider for a moment a single particle of light, a photon, born in the sun's core. It began as pure energy released by a fusion reaction in that dense, searing heart. For untold years, it fought its way through the sun's interior, scattering and dancing through the radiative maze, slowly migrating to the surface. At last, it broke free from the photosphere, joining the radiant tide of sunlight that floods out into the darkness. In that instant, it set out across the cosmic gulf at the ultimate speed, racing through the vacuum toward our small planet. After a brief voyage through the abyss of space, the photon pierces Earth's upper atmosphere. Perhaps it is dawn, and this tiny messenger of the day slips through a clear sky to reach a waiting leaf on a tree. The photon is absorbed, its energy triggering the chemistry of life, photosynthesis, helping a green leaf turn carbon dioxide and water into sugar. In that moment, a bit of the sun's energy, carried across the cold void by a single photon, becomes part of a living plant. Another photon falls upon a human face and is absorbed in the warm skin of someone standing under the morning sun. Nerves register the gentle heat. The mind welcomes the comfort. That warmth is a direct touch from our star, a tangible link between our flesh and the nuclear fires at the sun's heart. Every ray of daylight that we see, every soft beam reflected by the moon at night, began in the sun's core long ago. The sunshine that makes the petals of a flower glow, that draws a child's laughter on a bright afternoon, that dances on waves at dusk. All of it is energy forged in a star and sent outward as a gift across the emptiness. It is literally starlight. The light sustains the winds and rains of Earth's weather, drives the engines of life, and paints our world in color each sunrise and sunset. From the sun's perspective, these photons are a way it reaches into the darkness, touching worlds with its essence. From our perspective, they are life and time itself. Every meal we eat is sunlight captured by plants. Every sight we behold is enabled by the sun's illumination. Thus, the sunlight we feel on our skin carries an ancient story. It is the end of a journey that began in the heart of a star and a bridge between our everyday lives and cosmic processes. In that golden glow, the tumult of the sun's interior and the fury of its storms are gentled into a nurturing radiance that gives life rather than takes it. We are, in every sense, bathing in the light of a star. To stand in the sunshine is to be touched by the cosmos, to be warmed by a process that has been ongoing for eons. The next time you see dust motes dancing in a sunbeam or feel the sun's warmth on your face, remember that you are feeling the afterglow of a journey that spanned the depths of space and countless years, a journey from the core of a star to the core of your being. Beyond the orbit of Earth, the sun's influence continues in a quieter but no less significant form. The solar wind that billows out from the corona fills the solar system with a tenuous, invisible presence. Space is not truly empty. It is filled with the sun's breath. This stream of charged particles flows outward past all the planets, carrying with it a stretched-out imprint of the sun's magnetic field. It's as if the sun, through its wind, reaches out to touch each world in its orbit, linking them in a web of invisible threads. As the solar wind encounters each planet, the effects depend on whether the planet is protected by its own magnetic field or left exposed. We've seen how Earth's magnetic bubble deflects the wind, diverting the charged particles around us. Jupiter and the other giant planets have formidable magnetic fields that carve out even larger sanctuaries in the solar wind. When the solar wind presses against these magnetic bubbles, it sparks auroras at their poles too. Jupiter's polar skies glow with curtains of light far more intense than Earth's, and even Saturn wears ethereal rings of auroral light. On worlds like Mercury or our Moon, which have little or no magnetic shielding, the solar wind slams directly into the surface. It can embed particles in the soil and slowly sputter away atoms into space. Mars, with only patchy magnetic fields and a thin atmosphere, has its skies occasionally set aglow by diffuse auroras, a reminder that even without a strong magnetosphere, the solar wind still makes its presence known. Perhaps the most visually stunning evidence of the solar wind's reach is found in comets. When a comet from the frigid outer reaches of the solar system ventures close to the sun, it sprouts a luminous tail that always points away from the sun. This is because the solar wind, along with the gentle pressure of sunlight, is pushing material off the comet's nucleus and sweeping it into a tail that streams far into space. Every comet's tail is essentially a windsock, revealing the direction of the sun's breeze. In ancient times, people saw those mysterious comets with their glowing tails stretching across the sky, and perhaps sensed that the sun and the comet were interacting. Now we know it is the breath of the sun, gusting through space, that draws those ephemeral streaks. The solar wind is not a steady, featureless breeze. It has structure and gustiness. Fast streams of solar wind can overtake slower ones, creating turbulent regions out in the depths of space. Magnetic clouds and shock waves from solar eruptions course through the wind, eventually overtaking planets or other spacecraft that lie in their path. The wind also carries the sun's magnetic polarity outward. At times, Earth finds itself connected to the sun by magnetic field lines stretching across interplanetary space, allowing energetic particles from solar flares to spiral directly toward us. In this way, the solar wind is the medium that transmits the sun's influence throughout its domain, like a great cosmic ocean in which the planets sail. As our solar system journeys around the center of the Milky Way, it carries this protective bubble along. The sun, like a bee in a giant swarm, orbits the galactic core among billions of other stars. One lap around the galaxy takes an unimaginably long time. In the sun's long life so far, it has only managed a few dozen such circuits. On this grand voyage, our star drifts through changing cosmic neighborhoods. Sometimes the space around it is relatively empty. At other times it might encounter wisps of nebulae, or the lingering echoes of ancient supernovae. These encounters can subtly influence the boundary of our heliosphere, perhaps even nudge comets from the distant cloud at the fringes of our solar system. We ride along on this stellar odyssey, a family of planets wrapped in the sun's embrace, cruising through the galaxy's spiral arms. It is a humbling thought that our entire existence, every life, every story told under the sun, has been carried on this great galactic journey, and it will continue long after we are gone, the sun forging ahead through the dark with its tiny companions in tow. Eventually, at some immense distance from the sun, the solar wind begins to meet resistance. The sparse gas that drifts between the stars pushes back against the sun's advancing wind. The solar wind slows, compresses, and finally, at a certain boundary, it can push no further. The continuous expansion of the Sun's atmosphere is halted by the presence of the wider galaxy. This boundary marks the outer edge of the Sun's influence, the frontier of our star's dominion. Here, the solar wind's long journey ends, merging into the interstellar medium. This invisible border defines a vast bubble around the Sun, known as the heliosphere, a cocoon of solar particles and magnetic fields that envelops all the planets. To step outside that bubble is to enter truly interstellar space. For decades, the solar wind was only a theory, an idea to explain why comet tails always point away from the Sun. It wasn't until humanity ventured into space with probes that we felt this wind firsthand. Our spacecraft have measured its particles and tasted its composition. Finally, after decades of journeying, a tiny spacecraft built by human hands passed through the boundary of the heliosphere and sailed into interstellar space, becoming the first emissary from Earth to enter the realm between the stars. It confirmed the existence of that distant frontier and carried with it a golden greeting from our world as it moved under the dim light of a sun now far behind. The Sun's breath, it turns out, has a limit. Within that limit, within that bubble, the Sun is Lord and life-giver. Every world we have ever known lies inside this protective sheath blown by our star. Now, standing at the edge of the heliosphere, we gaze outward and backward to the realm of the galaxy beyond, and backward toward the Sun at the center of its bubble. We can appreciate the true scale of our star's influence. The Sun is not just a disk in our sky. It commands a vast region of space, sculpting it with light and wind. It has forged a safe haven in the galactic sea, a place where its family of planets resides. To understand the Sun fully, we must also understand how stars like it are born and how they die. For our Sun is one among billions, each with its own story of origin and fate. Our journey now moves beyond our solar system, beyond the present moment of our Sun's life, to the story of how such stars come into being and how they transform over time. Stars are born in darkness, far from the bright bustle of any galactic core, in the quiet spiral arms of galaxies like our Milky Way. Vast clouds of gas and dust drift in cold obscurity. These are the stellar nurseries, enormous nebulae stretching across light years of space, rich in hydrogen and sprinkled with heavier elements forged in ancient supernovae. Within these great clouds, gravity works patiently and silently. A slight densification, perhaps triggered by the shockwave of a distant exploding star or the brushing encounter of two clouds, begins to draw matter toward its center. As the gas compresses, it heats up and starts to glow faintly. What was once invisible in the darkness becomes a warm ember hidden inside a cocoon of dust. This is the birth of a star, or rather, the first whisper of a star yet to be. As the cloud fragment collapses under its own weight, it often breaks into smaller pieces, each destined to form a star, or even a small cluster of stars. In each fragment, matter spirals inward, and as it falls, it begins to spin faster, like a twirling ice skater pulling in her arms. A flattened disk of gas and dust forms around the growing central mass, whirling like a carousel. At the center of each collapsing fragment, a protostar, a baby star, is taking shape. It is not yet a true star, for it has not begun nuclear fusion, but it shines with the heat of its gravitational contraction. We can imagine it as a glowing orb buried deep within a dusty womb. If we could pull back the veil of dust and look inside, we would see a scene both serene and violent. The protostar's surface roiling with convection, jets of gas erupting from its poles and piercing out into space, and the surrounding disk feeding material steadily onto the growing stellar infant. In these concealed cradles, many stars are often born together, siblings in a stellar brood. Some are destined to be massive and brilliant, others small and faint. For a brief time, the protostar continues to gather mass. The infalling gas rains down mostly onto the disk, which then funnels onto the star. The star grows, and the pressure and temperature at its center climb ever higher. When the core temperature at last soars to the threshold, where hydrogen atoms begin to fuse into helium, a profound transformation occurs. The protostar becomes a star. It is as if a switch is flipped in its core. The darkness inside ignites into light. The star begins to generate its own energy by the same nuclear process that powers our sun, and a new sun bursts into existence in that once dark place. With that first ignition of fusion, a stellar wind, much like the solar wind of our sun, often springs from the newborn star, and intense light from the hot young star pours into the surrounding space. These forces blow away the remaining shreds of the natal cloud, dispersing the cocoon that once hid the star. If the star is massive enough, its fierce radiation may carve fantastic shapes in the parent nebula, creating glowing cavities and pillars of dust that resist the onslaught for a time. Before long, what was once an opaque dark cloud becomes a cluster of shining new stars, its birth cloud eroded to wisps around them. The siblings now bask in each other's light as they drift together, loosely bound by gravity. Our own sun was likely born in such a cluster of stars. It may have had many siblings forming alongside it in a long-vanished nebula, all of them cocooned together and then emerging into the galaxy's light. In that stellar nursery, the sun's siblings would have shone nearby, sharing a common region of space for a time. But over the ages, the cluster dispersed. Each star, including our sun, went its own way, moving through different orbits around the Milky Way. Today, the sun's sisters and brothers are scattered, indistinguishable from the other stars of the galaxy, though astronomers scanning the sky have identified a few stars with chemical fingerprints so similar to the sun's that they might be long-lost solar siblings. In the collapse of a nebula and the birth of a star, we see nature's cycle of creation at work. The gas and dust that form new stars carry the ashes of previous generations, the carbon that will someday course through the veins of living creatures, the oxygen that will fill their lungs, the silicon that will form rocky worlds. All these atoms were fused in stars that lived and died before our sun was born, then mixed into the clouds from which new stars arise. Each generation of stars enriches the galaxy further, seeding the raw material for planets and life. Thus, when a new star like our sun ignites, it carries within it the legacy of cosmic ancestry. Around many newborn stars, the leftover gas and dust in the disk coalesce into smaller clumps, giving birth to planets, moons, comets, and asteroids, the makings of a new solar system accompanying the new sun. From afar, a stellar nursery like the Orion Nebula offers us a glimpse of this wondrous process. Through telescopes, we see stellar embryos still swaddled in dust, others breaking free and burning blue-white with youthful energy. We see great columns of dark gas, cosmic pillars, being eroded by the radiation of hot young stars hidden within them. In that radiant chaos, worlds are being formed, and light that will shine for billions of years is first kindled. Star birth is at once delicate and cataclysmic. Delicate in the slow, inexorable gathering of a star's first light, and cataclysmic in the way a newborn star's brilliance can rip apart the very cloud that gave it life. From these nurseries emerge all stars, whether destined to be mighty blue giants or dim red dwarfs. The process is the same, guided by the pull of gravity and the laws of physics that govern heat, pressure, and fusion. We have journeyed from our sun's neighborhood out into the broader galaxy to witness the origin of stars. Now, having seen how stars take their first breath, we can explore the grand tapestry of stellar variety, the many kinds of stars that fill the cosmos, from the smallest embers to the most luminous beacons. The stars that populate the universe are as diverse as the creatures in a great ocean. They come in different sizes, colors, and brightnesses, each type with its own character. Astronomers classify stars by their temperature and luminosity, which often correlates with color. Just as iron glowing in a blacksmith's forge changes from dull red to orange to white hot as it gets hotter, a star's color tells us its heat. The coolest stars are deep red, smoldering with a subdued cherry glow. Hotter stars shine in yellow and white hues. The very hottest stars blaze with blue-white brilliance, their surfaces incredibly hot. The smallest true stars in the cosmos are the red dwarfs. These diminutive stars contain only a small fraction of the sun's mass and glow feebly, often with a light so faint that none are visible to the naked eye from Earth, despite being the most numerous stars in the galaxy. A red dwarf is usually much smaller and cooler than our sun, giving off a ruddy light. But what they lack in brightness, they make up in longevity and ubiquity. The vast majority of stars in the Milky Way are thought to be red dwarfs, quietly burning their fuel at a glacial pace. A red dwarf may live for an almost eternal span of time before it runs out of fuel. In these diminutive furnaces, the flame of nuclear fusion is weak but extraordinarily steady. Some of the smallest red dwarfs can continue to shine for longer than the current age of the universe. On the other end of the stellar spectrum are the blue giants and supergiants. These stars are born with many times the mass of the sun. They are extremely hot and brilliant, shining with a fierce blue-white light that can be seen across great distances. A blue giant star pours out an enormous amount of energy, consuming its hydrogen fuel at a prodigious rate. Because of this, its life is intense and fleeting. It will exhaust its core fuel in a cosmic eye blink, a mere moment compared to the tranquil longevity of a star like our sun. Some of these massive stars do not stay blue-white for their whole lives. As they age, they swell and cool, turning into red supergiants that can be truly colossal in size, their bloated atmospheres expanding outward to stupendous dimensions. Imagine a star so large that, were it placed where our sun is, it would extend beyond the orbit of Earth and well into the realm of Mars. These red supergiants glow with a cooler, reddish light, but they are tremendously luminous due to their sheer size. They are rare and splendid beacons in galaxies, heralds of impending cosmic change, for they live fast and die spectacularly. Between these extremes lies a rich variety of stars. There are orange dwarfs, slightly smaller and cooler than the sun. There are white stars, somewhat hotter and more massive than the sun. And there are stars like our own, yellow-white and medium-sized, often called main sequence stars or dwarf stars by astronomers. Our sun, in fact, is considered a dwarf star in this sense, not because it is especially small, it is larger and more massive than most stars, but because it is in the prime of its life, steadily fusing hydrogen in its core. It hasn't yet bloomed into a giant. In terms of mass and brightness, the sun is fairly average, but because the faint red dwarfs are so inconspicuous to our eyes, most of the individual stars that dazzle us in the night sky are actually more luminous than our sun. Many of the bright stars we see at night are larger, hotter, or more energetic than the sun, which is why they stand out from afar. Meanwhile, countless dim red stars nearer to us go unnoticed without a telescope. Stellar classification also includes exotic categories. There are the supergiants we mentioned, both blue and red, which are essentially stars on steroids, far larger and more luminous than ordinary stars. And there are stars at the very brink of not being stars at all, the brown dwarfs, sometimes nicknamed failed stars. These objects form in the manner of stars but do not accumulate enough mass to ignite sustained hydrogen fusion in their cores. A brown dwarf glows faintly with leftover heat from its formation, and perhaps with brief flashes of fusion of heavier forms of hydrogen, but it gradually cools and fades, acting more like a giant planet than a true star. Brown dwarfs fill the gap between the largest planets and the smallest red dwarfs, and they add to the menagerie of objects in the galaxy. Nature produces stars in a continuum of masses and sizes, from tiny red embers that burn for practically eternity to stellar titans that blaze with incredible intensity and then perish in the blink of an eye. Each type of star has its own destiny. A star's mass, set at birth, is the key that unlocks the rest of its life story. With a high mass comes a glorious but short-lived existence as a giant, likely ending in a dramatic explosion. With a low mass comes a long, steady burn and a quiet retirement. Having surveyed the variety of stars, the small, the medium, the great, we can now follow one typical star, perhaps not unlike our sun, through the stages of its life, from its youthful radiance to its final farewell. Let us trace the fate of a star much like our sun, now that it has burned in the heavens for eons. For a long time, such a star shines steadily, fusing hydrogen into helium in its core and bathing any nearby worlds in stable light. But the fuel at its center is finite. Eventually, after many billions of years of shining, the hydrogen in the core dwindles. The balance that sustained the star for so long begins to tip. With less fusion to support it, the core of the star starts to contract under its own gravity. As it contracts, it heats up, much as a bicycle pump grows warm when you compress the air inside. This extra heat flows into the shell of hydrogen that surrounds the inert core, a shell that still has hydrogen left to burn. And then something dramatic happens. Hydrogen in this outer shell, now at extreme temperatures thanks to the contracting core beneath, ignites in fusion. The sudden onset of shell burning causes the star's outer layers to push outward. The star swells enormously in size, turning into what we call a red giant. Its surface cools as it expands, shifting from yellow-white to orange-red. But the star's interior becomes hotter than ever, and its luminosity soars due to its sheer size. Our once modest sun-like star becomes a bloated colossus. In this red giant phase, the star's radius can grow far larger than it was in its youth. If our sun were to undergo this transformation, it would likely engulf Mercury and Venus, and perhaps even Earth, turning those worlds into charred cinders swallowed by the expanding stellar fire. The sky of any surviving outer planets would be dominated by the star's enormous disk, a brilliant coppery orb covering a huge swath of the heavens. Deep inside the red giant, the core continues to shrink and heat, as it is now made mostly of helium ash, the byproduct of those long ages of hydrogen fusion. When the core grows hot enough, a new kind of fusion begins. Helium atoms start fusing together to form carbon and some oxygen. Our star, which was facing death, finds a second wind. The onset of helium fusion in the core, often beginning in a sudden burst for a sun-like star, something astronomers poetically call the helium flash, stabilizes the star for a time. The core expands a little and cools, and the star's bloated outer layers contract somewhat from their extreme size. The star settles into a new equilibrium, a helium-burning giant. In this phase, the star's color might become a bit more yellowish as it slightly shrinks, and its surface temperature rises again, and it burns steadily once more, though its remaining lifetime is now comparatively brief. But helium, too, is a finite fuel. In time, the core's helium is exhausted, leaving an inert mass of carbon and oxygen, the carbon and oxygen that were created by the helium fusion. For a star like our Sun, no further fusion is possible in the core. The temperatures required to ignite carbon are beyond its reach. With fusion ceasing again in the center, the core of the star, now a dense ball of carbon and oxygen, contracts yet further. Meanwhile, helium fusion may continue in a shell around the core, with hydrogen fusion still going in a shell above that for a while. This causes the star to swell once more, even larger than before. The giant star becomes highly unstable in this final stretch of its life. It pulsates, growing and shrinking, trying to find balance, but never quite succeeding. Each expansion and contraction shakes loose some of the star's outer layers. Gentle at first, these pulsations turn into violent throes that throw vast clouds of the star's outer atmosphere into space. The star is literally coughing away its own substance, shedding its mass like tears into the void. Eventually, the entire outer envelope of the star is cast off, blown away into space as a gorgeous gossamer shell of gas. For a brief time, that expanding shell is illuminated by the hot, exposed core at the center, and it shines as a glowing, multicolored cloud known as a planetary nebula. To an observer afar, it is a sight of eerie beauty. A round or ring-shaped mist, glowing where once there was a star, often with intricate patterns like delicate rings or hourglass forms. This is the dying breath of a star like the sun, a final gesture of beauty as its outer layers, now free in space, fluoresce in the stellar twilight. What remains of the star itself is the central core, now revealed, a ball of carbon and oxygen about the size of Earth, tremendously hot but no longer sustained by fusion. This is a white dwarf, the ember of a star's heart. It glows white-blue with residual heat, initially extremely hot, though its small size means its total light output is relatively modest. A white dwarf is one of the strangest forms of matter in the universe. It is supported not by heat or ongoing fusion, but by the quantum pressure of electrons, a fundamental resistance of matter to further compression. Its density defies imagination, the mass of a sun compressed into a sphere the size of a planet. A spoonful of white dwarf material would outweigh a mountain. In this exotic, degenerate state, the stellar core will sit and slowly cool for time spans beyond human comprehension, fading from white to yellow to red, and eventually toward blackness. Thus ends the life of a sun-like star, not with a bang, but with a serene, farewell glow. The mighty red giant's cast-off shroud becomes part of the galaxy, seeding space once more with elements like carbon and oxygen that will one day find their way into new nebulae, new stars, new planets, and perhaps new living beings. The white dwarf that remains is like a stellar tombstone, an extremely dense crystal of carbon and oxygen. Some have likened a white dwarf to a cosmic diamond, marking where a shining sun once lived. Over eons, it will cool further and dim, eventually becoming a black dwarf, a hypothetical cold dark sphere, the final quiet cinder of a once radiant star. The universe, however, is not yet old enough for any white dwarfs to have cooled completely to black. That final stage lies in the far future, far beyond the present age of the cosmos. Our sun will one day follow this very path. It is the destiny of all stars in its weight class. But not all stars share the same fate. The most massive stars, those bright blue giants we discussed, live dramatically different lives and meet far more violent ends. Before we return to the personal tale of our own sun's future, let us first briefly touch on the spectacular final act of those heavier suns, a fate that leaves behind some of the most enigmatic objects in the cosmos. While a star like the sun ends its life in relative peace, the same cannot be said for the giants. The most massive stars go out with staggering violence. After burning through hydrogen and helium in a cosmic rush, a high-mass star, far more massive than our sun, doesn't stop at carbon and oxygen. Its core, under tremendous gravity, continues fusing heavier and heavier elements in layers, like the layers of an onion. Carbon fuses into neon, neon into oxygen, oxygen into silicon, each stage burning faster and yielding less energy than the last. Finally, the core is transmuted into iron, the ash of nuclear fusion, an element that cannot release energy by fusing further. When enough iron accumulates in the core, the the star faces an irreversible crisis. With no new energy to support it, the iron core collapses in on itself in a fraction of a second. The core implodes, and densities reach such extremes that atoms are crushed. Protons and electrons melt into neutrons. The core, which was once perhaps the size of Earth or smaller, shrinks to a sphere only a few miles across in an instant. In that moment of collapse, a phenomenal amount of gravitational energy is released. The infalling outer layers of the star hit this super-dense core and rebound outward in a titanic explosion, a supernova. The star's death throes are so violent that for a brief time, the exploding star can outshine all the billions of other stars in its galaxy combined. The supernova blasts the star's outer layers into space at incredible speeds, and shockwaves race through the expanding debris. Temperatures in the explosion briefly soar so high that elements heavier than iron are forged in the fiery crucible. Gold, silver, uranium, and many others are synthesized in those final furious seconds. These newly minted atoms are hurled into the cosmos to mingle with the gas and dust that will eventually form new stars and planets. What remains at the center of this cataclysm is the collapsed core. If the star was only moderately massive, on the lower end of the massive star range, the core's collapse is halted by the pressure of densely packed neutrons. Matter squeezed so tightly that the neutrons resist any further compression. The core becomes a neutron star, an object of incredible density and exotic nature. A neutron star packs more mass than our Sun into a sphere only a few tens of miles wide. It is essentially a giant atomic nucleus, a ball of neutrons left behind by the supernova. A thimbleful of neutron star material would outweigh a mountain. Neutron stars often spin rapidly. The parent star's rotation speeds up dramatically as it collapses, like a pirouetting skater pulling in her arms, and they may possess intense magnetic fields. Some neutron stars sweep beams of radiation from their magnetic poles as they spin, like lighthouses in the cosmos. These are observed as pulsars, blinking radio or X-ray beacons, marking the location of a neutron star across the galaxy. For the most massive of massive stars, even neutron degeneracy pressure cannot hold the core up. If the collapsed core is above a certain critical mass, nothing known can stop its collapse. It continues to shrink until it essentially vanishes from view, forming a black hole. In that case, the stellar remnant has crushed itself into a point of virtually infinite density, enveloped by a region of space from which nothing can escape. Not even light can climb out of the warped space around the collapsed core, hence the name black hole. What was once the heart of a star becomes a kind of cosmic abyss, a pit in the fabric of the universe. A black hole can be thought of as the star's ultimate tombstone, carrying its mass hidden within a distortion of space-time. We infer its presence only by ghostly tracers, the desperate whirl of gas and dust spiraling into invisibility, flaring in X-rays as it vanishes, or the subtle quivering of space-time itself when the black hole is jarred by the fall of something massive. When a supernova finally fades, it leaves behind these strange remnants, a neutron star or a black hole, and an expanding cloud of gas and dust that was once the star's outer layers. In time, that cloud will cool and disperse into the interstellar medium. The elements cast into space will blend with other matter and eventually become part of new stars, new planets, and perhaps new life. Massive stars, though few in number compared to red dwarfs, are the great alchemists and fireworks of the universe. In dying, they sow the heavy elements across the galaxy, the very elements that make rocky planets and organic beings possible. Every atom of calcium in your bones, of iron in your blood, was forged in the belly of a star that ended in such a blaze. The cosmic ashes of supernovae fertilize the galaxies, ensuring that each new generation of stars is born with a richer array of ingredients for planets and for life. We have traced the lives of stars from gentle birth in nebulae to either a quiet sunset as a white dwarf or a cataclysmic finale as a neutron star or black hole. But our exploration of suns would be incomplete without considering that stars rarely live in isolation. Most have companions or families of their own, multiple star systems bound in gravitational dances, or retinues of planets that circle around them. Our sun itself has a family, the planets, including Earth, and smaller bodies that formed from the disk of dust left over from the sun's birth. And many stars form in pairs or trios, locked in orbits around each other. To truly understand the nature of suns, we must also look at these relationships, the celestial communities that stars form, and the diverse planetary systems that have arisen around distant suns. Each star in the night sky is a sun in its own right, and many are far from solitary. In fact, most stars are born as multiples, two or more suns bound together by gravity, orbiting a common center. Imagine a binary star system, two suns locked in an elegant dance, circling each other over years or centuries. From a distance, they might appear as a single point of light, but up close, each partner star swings through space in response to the other's pull. Some binaries are widely separated, each star carrying its own retinue of planets. Others whirl so close that they can trade gas, or even, in extreme cases, merge into one. In a triple or quadruple system, the dance grows even more complex, with stars tracing intricate paths around their mutual center of mass. The universe is a grand stage, with every stellar configuration you can imagine. There are suns that eclipse one another from our viewpoint, causing their combined light to rhythmically dim and brighten, cosmic beacons signaling their orbital waltz. There are stars so close that they share a common envelope of gas, two stellar hearts wrapped in one glowing shroud. And there are systems where small companion stars orbit giant ones in distant loops, like tiny sparks flitting around a great flame. Around many of these suns, planets coalesce and circle, for planet-making is a natural companion to star-making. When a star is born from a spinning disk of dust and gas, the leftover material often forms worlds. Our own solar system is one example, a handful of major planets and a retinue of smaller bodies. And we have learned that planets are astonishingly common. We now know that planets accompany stars throughout the galaxy. Astronomers have discovered innumerable exoplanets orbiting distant suns, and they suspect that for every star we see, there are likely worlds in attendance. There are planets that cling close to their stars, scorched and locked by gravity, so that one hemisphere endures endless day while the other is in perpetual night. There are planets at just the right distances from their suns, the so-called habitable zones, where conditions might allow liquid water and the chemistry of life. Some planets orbit twin suns, experiencing double sunrises and double sunsets, their skies graced by two stellar disks. Imagine standing on such a world, with two faint shadows dancing on the ground, or on a world under a dim red dwarf sun, where the daylight is a brooding ember, and the stars' frequent flares paint the sky with sudden ruddy hues. Each planetary system is a story of creation, just as every star's life is a story. Some stars have giant guardian planets that shield inner worlds from comet bombardments, as Jupiter helps shield Earth. Others have planets in wild, elongated orbits, leading to chaotic swings of climate. Some massive stars might not host long-lived planets at all, as their fierce radiation and short lives can blast away or outlast any nascent worlds. But around the more common, steady stars, the red dwarfs, the orange dwarfs, the sun-like stars, there are surely many planets that have persisted for eons, perhaps even giving rise to life. Under alien suns, if life has blossomed, creatures might gaze up and see a sky tinted by a different color of star and wonder about the warmth that gives them life, just as we ponder our sun. For us, those other suns have been points of curiosity and imagination, for as long as we've had eyes to see the stars. Only recently have we begun to detect some of their planets directly, to see the telltale dip in a star's light as an orbiting world passes in front of it, or to measure the slight wobble of a star tugged by the gravity of unseen companions. Each discovery is a revelation, proof that our sun and its family are not unique, that the cosmos is filled with solar systems. It humbles us, yet also makes the universe feel more intimate. A place where countless stars shine down on their own worlds, as the sun does on ours. Now, after journeying so far through stellar nurseries, fiery demises, and distant solar systems, we return our focus to our own star, the sun, and reflect on its ultimate destiny, and on what it means for us to live beside a star. And so we return to our sun, the star that has accompanied every moment of humanity's existence and that sustains all life on Earth. The sun today is a middle-aged star, steadily burning its fuel and kindly bathing our world in light. It has shone in our skies for longer than any living thing can remember, and will continue to shine for ages to come. But the sun, too, is mortal in the cosmic sense. Nothing in the universe lasts forever, not even a star. In the far future, long after our species and all we know may have turned to dust, the sun will begin to change. When its core can no longer sustain the fusion of hydrogen, it will respond by growing in size and luminosity. Our sun, so familiar and constant, will swell into a red giant. Its light will turn the color of copper and blood, and it will loom colossal in the sky. The innermost planets will be engulfed in its fire. Mercury and Venus will surely be devoured. Earth may meet the same fate, or be left a charred and barren rock, its oceans boiled away, its surface desolate and scorched. For any life remaining then, these changes will be catastrophic beyond measure. But likely, by that distant era, Earth will already be quiet and lifeless, or life, if intelligent and capable, will have found refuge elsewhere. The sun, once a gentle guardian, will become an inexorable destroyer of the very life it once nurtured. Yet even in this fierce transformation, there is a strange grandeur. As the sun's red giant phase reaches its climax, it will cast off its outer layers. Our star will shed its shining mantle, which will expand outward, drifting into space. For a short time, those cast-off layers will form a beautiful planetary nebula around the dying sun, a glowing testament to its passing glory. Future astronomers, perhaps from other surviving worlds or civilizations yet unimagined, might look toward our solar system and see a delicate shell of gas, like a cosmic flower blossoming and fading, shining in remembrance of the star that was. At the center of that nebula will remain the sun's core, now exposed and shrunken to a white dwarf. This final stage of our sun's life will be a small, hot sphere no larger than Earth, composed mostly of carbon and oxygen. The sun's very heart, left glowing like a lonely ember in the night. It will shine white and then blue-white, slowly cooling over the course of billions of years. The brilliance of the day that once was will recede into a gentle twilight. The white dwarf sun will illuminate the ghostly nebula for some thousands of years, but eventually it too will fade, perhaps becoming a black dwarf in the far, far future. The solar system will drift in darkness and silence. This is the ultimate fate of our sun, to swell in glory and then to divest itself of its brilliance, leaving behind a small, dense core that will quietly glow and then dim to darkness. It is a fate that the sun will meet far in the future, an inconceivable gulf of time beyond our lives. In knowing this, we find both melancholy and solace. Melancholy that all things we know are transient, that even the great sun will one day wither and leave the sky empty. Solace that we and our world have yet long epochs in which to live under the sun's light, and that when the end comes, it will be part of the natural order of the cosmos. The same finale that countless sun-like stars have already played out in the quiet reaches of the galaxy. And perhaps, too, there is a kind of triumph in this ending. The sun's final nebula will return its substance to space, enriching the interstellar clouds with elements that once made up Earth and us, and every living thing that sunlight ever touched. In that way, the sun's death will seed new beginnings elsewhere. Some of the carbon and oxygen from the sun's core might drift for ages and eventually become part of new stars, new planets, new life. As it has always been in the universe, one star's end is another's beginning in the endless cycle of creation. Now, stepping back from this entire journey, from the birth of stars in dark nebulae to the blaze of supernovae, from the quiet glow of the sun's youth to its fiery demise, we find ourselves contemplating what it means to be the children of a star. To live beside a star is to live in a state of grace between wonder and knowledge. We orbit a massive, luminous being that gives us everything: light, warmth, the very possibility of life, and yet asks nothing in return. Our ancestors felt the sun's power and worshipped it. They built legends and monuments to honor it. We, with all our modern understanding, have not lost that reverence. How could we? Each dawn when sunlight spills over the horizon, painting the sky in rose and gold, we feel the same awe that ancient watchers felt as the morning star ascended. In that daily miracle, night yields to day, cold yields to warmth, and the world is renewed. We know the science of it. The earth is turning, bringing us once more into the sun's light. But knowing takes nothing away from the magic of feeling it. Beneath the facts and figures, there is a simple truth. The sun is the source of our being. Every meal we eat is sustained by sunlight captured by plants. Every warm breeze that caresses our skin, every drop of rain that falls, is driven by the sun's heat, nurturing our planet. And our bodies themselves are made of material created in long-dead stars and powered by the sun's current light. We truly are made of stardust, shaped into conscious form and given the spark of life by a star's energy. In a very literal sense, we are children of the stars. When we say we are born of starlight, it is not just poetry, it is lineage. The elements in our flesh were brewed in stellar furnaces, and the energy that ignites our living cells is a gift from our sun. Our story and the sun's story are inseparable. Think of the connection. A baby born on a bright morning, crying out with lungs filled for the first time. Those lungs draw in oxygen that a star, billions of years ago, forged in its core and then cast into space. The baby's parents smile in the sunlight that streams through the window, sunlight that left the sun just moments earlier, having traveled across empty space to fall upon that new face. A chain of events spanning eons and light years has culminated in that ordinary, extraordinary moment. Starlight becomes life. The cycle continues. Standing here on Earth, we look up and see a blue sky by day. But beyond that blue lies the black tapestry of space and the brilliant stars. Our sun is one among many, and though we cannot see those others by day, they are there, distant and shining. At night, when our sun has set, we glimpse the wider cosmos of which our star is a part. We see the Milky Way's misty band, made of uncountable suns, and we realize that our little home orbits just one humble star on the edge of a vast galaxy. The humility of this perspective is profound, yet it does not diminish us. It elevates us. We are part of something immense and beautiful. The stars that speckle the night sky are our cousins. Some may have planets with beings who look up at their own sun and feel the same wonder. In the end, the story of suns is the story of creation itself. It is an ancient tale, told in the language of light and gravity. It began before we were here and will continue long after we are gone. But for a brief moment, we get to be conscious participants in this grand drama. We get to study the sun, protect ourselves from its tantrums, bask in its warmth, and dream under its light. Our lives, like mayflies, flicker in the daylight of this star. But while we are here, we behold the splendor of the cosmos through the window that our sun's light provides. As we conclude this journey, imagine once more the sun hanging low at dusk. The sky blazes with color and the shadows grow long. In that sunset is a reflection of the entire epic. Day turning to night as stars appear one by one, the cycle of light and dark that has guided life's rhythm from the beginning. The sun will rise again tomorrow, as it always does, bringing a new day. But even when it eventually rises no more, the legacy of its light will live on in everything it touched. We live on the brink of a star's fiery grace, taking our nourishment from its hand and daring to learn its secrets. We are small, but we are also a way for the universe to know itself. Matter that was once scattered across space, now gathered and alive, pondering the star that gave it life. In the dance of sunlight and shadow, we find meaning, comfort, and inspiration. Our sun connects us to the universe and to each other, a common star, binding all living things in a shared radiance. So when you next stand in daylight, feel that warmth and remember, you are heir to an ancient covenant between earth and sun. Every photon that touches you carries a message from that central fire, that life is precious and intertwined with the cosmos. Our world exists because a star shines. And in the atomic hearts of stars, in the silent roaring of their nuclear fires, in the gentle glow that crosses the void, the universe has found a way to nurture consciousness and wonder. This knowledge, this feeling, is humbling and uplifting all at once. The saga of suns is indeed a cosmic poem, forged in light, breath, and gravity. It is written across the heavens in the glow of nebulae and the ashes of supernovae, in the rising of each morning sun and the eternal glitter of the night. It is a poem we are part of, every one of us made of star stuff and sustained by starlight. In knowing this, we find not despair at our smallness, but gratitude and awe that we have the privilege to dance in the light of a star, and through that light, yet we hardly grasp its magnitude. Everything is the totality of existence, the stars and galaxies, time and space, energy and matter, life and mind. It is all that is, all that ever was, all that ever will be. In its embrace are the quiet dust under our feet and the shining furnaces of distant suns, the hum of a thought and the roar of a supernova. To contemplate everything at once is to stand at the shore of an infinite ocean, awed and humbled. Even our most fleeting reflection on the cosmos can send a shiver down the spine, as if some deep part of us remembers that we are a part of this grand tapestry, woven into its very fabric. On a clear night, under a vault of stars, we gaze upward and attempt to fathom our place in a vastness without obvious bounds. We see pinpoints of light scattered across a canvas of darkness, each a sun, perhaps with its own planets and stories. We feel small, yet we are connected to all of it. The iron in our blood, the calcium in our bones, the carbon in our DNA, these were forged in the hearts of ancient stars. We are children of the cosmos, built of its matter, energized by its light, and guided by our curiosity to understand it. Through science and imagination, we stretch our minds toward the edges of the universe, seeking to grasp how all of this came to be. From time immemorial, we have gazed at the heavens and spun stories about our place among the stars. Today, our tools are telescopes and equations, but the sense of wonder remains as profound as ever. In this journey, we will blend science and poetry, fact and metaphor, as we explore the cosmos on every scale. We will touch on cosmology and physics, astronomy and mathematics, philosophy and human curiosity, all the lenses through which we seek understanding. Together, let us venture to the very beginning of time and back, and to the farthest reaches of space, in pursuit of the story of everything. Our journey begins at the very beginning, at the origin of everything we know, in the primordial darkness, before a single star had ever shone. All that would become the universe was cradled in a point smaller than an atom. It is nearly impossible to imagine. A seed of unimaginable density and heat. A single point that held the potential for galaxies, for life, for every atom and every moment in time. And then, in an instant about 13.8 billion years ago, that seed exploded into growth. There was a flash of pure creation, a moment we call the Big Bang. Time and space themselves were born in that moment. What had been nowhere became everywhere. What had been nothing became everything.
The newborn universe expanded with incomprehensible fury. In a tiny fraction of a second, it swelled from microscopic to cosmic scales. This extraordinary growth spurt, known as cosmic inflation, stretched space like a balloon inflating at faster than light speed. Distances between points grew by an enormous factor, smoothing out any clumps or curves. Inflation explains why the universe today is so uniform and flat on large scales. It was as if any initial wrinkles in space were ironed out by this tremendous expansion. A smooth, seething fireball emerged from that initial burst. Tiny quantum fluctuations, random little flickers of density in that early vacuum, were blown up by inflation into slight variations in the otherwise even spread of matter. These faint imprints would one day guide the formation of galaxies, but for the moment, the infant universe was a hot, dense soup of energy. As inflation settled, the energy driving it transformed into matter and light. The universe was 1 second old. In that first second, space was filled with an intense, blinding glow, radiation so hot that it would have vaporized anything, though as yet, there was nothing but fundamental particles. Matter and energy were not yet distinct. They flowed together in a plasma, a fluid of raw creation. Protons and neutrons jostled in temperatures of billions of degrees. In the minutes that followed, the entire universe itself became a nuclear reactor. These building blocks began to combine in countless tiny nuclear forges across the young cosmos. Protons fused with protons, neutrons linked with protons. By 5 minutes of cosmic time, the first atomic nuclei had formed. The simplest elements came into being: hydrogen, the lightest of all, and helium, its slightly heavier kin. A trace of lithium also appeared. In that brief early epoch of nucleosynthesis, the universe forged the basic chemical foundation it would use to build everything else. About 3/4 became hydrogen and 1/4 helium by mass, an elemental newborn universe. Still, no atoms as we know them could yet exist. The universe was far too hot for electrons to settle into orbits around nuclei. Instead, electrons careened freely through the dense plasma, scattering light incessantly. Photons, the particles of light, were trapped in a cosmic fog, bouncing from one free electron to another. Space glowed as bright as the interior of a star, but no light could travel far. The universe was opaque, a brilliant radiance suffused within a swirling, glowing mist. As seconds turned to minutes, minutes to hours, and hours to years, the young cosmos continued to swell and cool. Hundreds of thousands of years passed. Expansion took its toll on the fireball, diluting and cooling it steadily. At around 380,000 years after the Big Bang, a critical threshold was crossed. The temperature fell enough that electrons could finally be captured by nuclei. Protons clutched electrons to form hydrogen atoms. Helium nuclei gathered electrons to become helium gas. This transition is called recombination, though it was the first time such combination had occurred. With electrons now bound into atoms, the fog lifted. The once captive light was free at last. In every direction, a brilliant afterglow burst forth and raced away through space. The universe that had been opaque became transparent.
That first light still surrounds us today. It has cooled to a gentle microwave glow that bathes the entire sky. The cosmic microwave background, the oldest light we can see. Back then, it was a searing, orange-white illumination everywhere. As space expanded and cooled, that light's wavelength stretched beyond red, through infrared, and into the microwave part of the spectrum we detect today. Discovered as a faint hiss in radio antennas, this afterglow is a whisper from the time the universe took its first breath as a transparent cosmos. The universe then entered a deep, dark age. With the primal light released and streaming onward, space itself went dark. There were not yet any new sources of light. The primordial gases, mostly hydrogen and helium, now drifted through expanding space like a vast, invisible fog. Gravity, the great sculptor, began to gently tug on the ever-so-slight variations in density left by inflation. Regions that were just a bit denser than average exerted a stronger pull, drawing in matter from their surroundings. Invisible threads of gravity started weaving patterns in the darkness. Over tens of millions of years, those threads pulled gas into clumps. The silent clouds grew denser and tighter until, at last, there was fire again. Perhaps 100 million years after the Big Bang, the first stars were born. Deep in massive collapsing clouds of hydrogen and helium, the pressure and heat ignited nuclear fusion. Starlight pierced the darkness. These first stars were giants, short-lived behemoths burning hot and blue, forging heavier elements in their cores as they shone. They lived for only a few million years before dying in titanic supernova explosions, seeding the surrounding space with the new elements they had cooked up: carbon, oxygen, nitrogen, iron. Ingredients that one day would be essential for planets and life. The death of each star sent enrichment into space, and out of the ashes, new generations of stars would eventually form. Their brilliant ultraviolet light also gradually burned off the primordial hydrogen fog in intergalactic space, rayonizing the cosmos and allowing light to travel freely everywhere. With the birth of stars, the cosmos had begun to light up structure by structure, ending the long night of the Dark Ages. The cosmic dawn gave way to a growing day as the first stars and nascent galaxies illuminated the heavens. As stars gathered, they formed the first proto-galaxies, small galactic building blocks that later merged into larger ones. Gravity continued its tireless work on grander scales. Stars bound themselves into galaxies, and galaxies gravitated into clusters. Over hundreds of millions, and then billions of years, a vast cosmic web took shape. Galaxies pulled on one another along filaments of invisible matter, collecting into chains and sheets. Imagine a spider's web made not of silk but of galaxies, strung along invisible filaments, with enormous voids of near-empty space in between. Astronomers mapping millions of galaxies, for instance in the Sloan Digital Sky Survey, have unveiled this vast cosmic web in detail, huge filaments like the Sloan Great Wall stretching across hundreds of millions of light-years, and immense voids nearly empty of galaxies. It serves as the large-scale structure of the universe. Galaxies grouped like sparkling dew on cosmic threads, clusters at their intersections, and between them, great dark gaps where few galaxies shine. Interestingly, researchers have even drawn analogies between the cosmic web and biological systems. One experiment showed that a slime mold, when presented with simulated galaxy clusters as nutrient sources, grew tendrils that closely traced the filaments of the cosmic web, as if nature repeats patterns on vastly different scales. From a vantage point far away, the universe would look foamy or spongy, matter gathered into fibrous clusters surrounding empty cavities. And within each galaxy, countless stars swirled, orbiting their galactic centers like bees around a hive. What about the universe as a whole? Is it shaped like a sphere, a saddle, a donut, or an infinite flat expanse? As far as we can discern,
Space on the largest scales is remarkably flat, like an endless plane. If you set off in a straight line among the galaxies, you would not curve back around to where you started, at least not within any distance we can observe. The cosmos could extend forever, infinite in extent. It might also be finite yet unbounded, curving back on itself only on scales beyond our observational reach, rather like the surface of a balloon is finite, yet has no edge. Current measurements of cosmic geometry show no significant curvature. To the best of our knowledge, parallel beams of light travel straight and never meet. It is currently unknown whether the universe might eventually loop back in some topologically complex way, like a 3D torus. But if it does so on a scale far larger than the observable horizon. In all directions, space stretches out similarly, giving us no hint of an edge or a boundary. We are, however, limited in what we can see, not by any solid wall at the universe's edge, but by time itself. The observable universe is a sphere around us, about 46 billion light-years in radius, delineated by the distance light has been able to travel since the Big Bang. We can only see as far as the light that has had time to reach us. Beyond that horizon, light from those regions has not yet arrived, and perhaps never will. Thus, we gaze out at a bubble of the universe around us. Beyond it, the mystery continues, perhaps with more galaxies and more cosmic web stretching indefinitely, or perhaps something radically different. For now, it remains hidden, a tantalizing unknown just out of reach. The cosmic horizon is not only a physical limit, it's also a reminder of our cosmic myopia. It's like standing on the shore of a vast ocean at night. We see the dark waters meet the sky at the horizon and wonder what lies beyond. Our cosmic horizon is such a shore, and though we cannot see past it, we imagine an endless sea beyond. Even as structures formed and stars lit up, the overall expansion of space never halted. The universe kept stretching, carrying galaxies farther apart from each other. The very fabric of space is like an ever-expanding canvas, and the galaxies are like dots of paint on that canvas, drifting away as the canvas grows. The light that travels between galaxies is stretched too. As space expands, wavelengths of light elongate, shifting toward the red end of the spectrum. Thus, when we observe distant galaxies, their light is reddened, a cosmological redshift that encodes their motion through the expanding space. In the early 20th century, astronomers armed with new telescopes made a profound discovery. Nearly all galaxies beyond our local group are racing away from us, and the farther they are, the faster they recede. Edwin Hubble measured this relationship, finding that the speed of recession is proportional to distance. Today, this rate of expansion, known as the Hubble constant, is roughly 70 kilometers per second per megaparsec, meaning a galaxy about 3.3 million light-years away recedes at roughly 70 kilometers, and one twice as far at about 140 kilometers. This linear relationship, now called Hubble's law, was revolutionary evidence that the universe is expanding uniformly in all directions. It is not that we are at the center of an explosion, but rather that space itself is swelling, so every galaxy sees others moving away. Imagine raisins in a rising loaf of bread. Each raisin sees the others receding as the dough between them expands. Just so, our Milky Way and all galaxies are like raisins embedded in the expanding space of the cosmos. Yet even as Hubble and others revealed an expanding universe, other observations soon uncovered a deeper mystery in those galaxies. In the later 20th century, astronomers like Vera Rubin noticed that stars at the outskirts of spiral galaxies were orbiting their galactic centers at startling speeds, too fast to be explained by the gravity of the visible stars and gas alone. According to Newtonian physics, those outer stars should have been flung off into space, or conversely, one would need far more mass in the galaxy to hold them in their orbits. Something unseen, some additional gravitating mass, was providing the extra pull. Similarly, clusters of galaxies were found to contain far more gravity than the visible matter could supply. It was as if an invisible halo of mass surrounded clusters and individual galaxies alike. This mystery substance was dubbed dark matter. It does not shine or interact with light, making it invisible and detectable only through its gravity. But it is abundant, far more abundant than the ordinary matter we see. Roughly 85% of the matter in the universe is dark matter, about 5 times more mass than in normal atoms. It acts as the scaffolding of the cosmic web. It clumps under gravity, forming massive halos, and ordinary gas falls into those halos to form galaxies. Without dark matter's guiding hand, the universe would lack much of the structure we observe. Galaxies might not have had enough gravitational glue to coalesce as they did. We even observe gravitational lensing, light from distant objects bending around invisible mass, revealing dark matter's presence. In colliding galaxy clusters like the Bullet cluster, the normal matter, hot gas visible in X-rays, can be seen to separate from where most of the gravity is. The gravitational center follows the unseen dark matter, providing direct evidence of this hidden mass. We still do not know what dark matter is. Perhaps some as yet undiscovered elementary particle that interacts only weakly with normal matter, often hypothesized as WIMPs or axions, or something more exotic like primordial black holes or a modification of gravity itself. Experiments deep underground and in particle accelerators are attempting to detect dark matter particles directly, so far without success. For now, we infer dark matter's presence by how it holds galaxies together and how it tugs on light passing by. It is the universe's invisible skeleton, a shadowy scaffolding that shaped the beautiful pattern of galaxies and clusters, all while remaining hidden from our eyes. As if dark matter were not mysterious enough, an even stranger ingredient dominates even that. For a long time, scientists assumed that the expansion of the universe, while continuing, should be slowing down over time. After all, gravity pulls all matter together. The collective gravity of galaxies, dark matter, gas and stars should gradually tug at the expansion, perhaps even causing it to reverse in the far future. But in 1998, 2 teams of astronomers observing distant type Ia supernovae, exploding stars used as standard candles, made a shocking discovery. The supernovae were dimmer and farther away than expected, indicating that the expansion of the universe was not slowing at all. It was speeding up. Over the last few billion years, the galaxies have been accelerating away from each other. Some kind of force or energy inherent to space is pushing them apart. Decades earlier, Albert Einstein had introduced a cosmological constant into his equations of general relativity to allow for a static universe, not realizing the universe actually expands. When Hubble's expansion came to light, Einstein reportedly called that constant his greatest blunder. But now, the accelerating cosmos implies something like Einstein's constant truly exists after all. We call this phenomenon dark energy, a name that signifies how little we truly understand it. Dark energy appears to be a property of space itself. Every cubic centimeter of vacuum seems to carry a minuscule amount of energy that, summed over billions of light years of emptiness, dominates the universe. Today, roughly 68% of the universe's total energy content is this dark energy, with about 27% dark matter and only 5% normal matter composing the rest. It behaves almost like an anti-gravity, driving galaxies apart on large scales and overpowering the attractive force of gravity at cosmological distances. Perhaps dark energy is a fixed property of the vacuum, a realization of Einstein's cosmological constant, or perhaps it changes over time, a dynamic field dubbed quintessence. Upcoming observatories and surveys are dedicated to measuring the expansion history more precisely, in hopes of discerning the true nature of this mysterious energy. For now, dark energy remains an enigma at the heart of cosmology, a gentle but inexorable push woven into the fabric of space-time. What does an accelerating expansion mean for the future? The fate of the universe hinges on dark energy's nature. If dark energy remains constant, a steady push that continues indefinitely, then the expansion will not only continue, but accelerate forever. Galaxies that are not gravitationally bound to us will recede faster and faster, eventually zooming away at such speeds that their light can no longer reach us. In tens of billions of years, distant galaxies will disappear beyond our horizon, leaving only the gravity-bound local group of galaxies, by then likely merged into one large galaxy, visible. If we look far, we'll see darkness where once galaxies twinkled. Over extremely long timescales, the stars within our remaining galaxy, or merged Milky galaxy, will age and die. New stars will form more slowly as the available gas becomes sparse. Trillions of years from now, the last stars will exhaust their fuel and flicker out one by one, leaving a universe populated only by faint stellar remnants, white dwarfs cooling to black, neutron stars, and black holes. The cosmos will grow colder and darker as eons pass. Eventually, even black holes will evaporate via Hawking radiation, on timescales so vast, 10–100 years or more, that they defy imagination. What remains will be a thin haze of fundamental particles and energy, spread so dilute that for any given volume of space, on average, there might be essentially nothing in it. This is the Big Freeze or heat death scenario, a universe that expands forever while cooling asymptotically toward absolute zero, approaching a state of maximum entropy where no organized energy remains to do work. If an astronomer were alive in that far future of a Big Freeze, they would see a very different sky. Beyond our small gravitational neighborhood, no galaxies would be visible at all, only an endless black void punctuated by the occasional faint glow of a red dwarf or the spark of a distant supernova, becoming rarer with time. The evidence of the Big Bang itself would fade. The cosmic microwave background, which today is a cool 2.7 K glow, would be stretched to radio waves so long and weak as to be undetectable. The chemical elements would slowly transmute as protons perhaps decay over immensely long times, if proton decay is a real phenomenon. Eventually, it would be a universe of scattered particles and low-energy photons, drifting in an ever-growing silent darkness. Time would continue, but virtually nothing of interest would happen. It is a state as close to true cosmic stillness as can be. The universe would have effectively died, not with a bang, but with a long, drawn-out whimper. There are even more violent speculative possibilities. If dark energy is not constant but instead grows stronger with time, imagine a form of phantom energy, then the acceleration would steepen catastrophically in the far future. In such a scenario, the repulsive effect of dark energy could increase without bound. One could imagine the final moments of such a universe. Galaxies rush away from each other at ever-increasing speeds. Eventually, in the distant future, the expansion's pull becomes so strong that it overcomes the gravity holding galaxies together. First, galaxy clusters are pried apart. Later, the galaxies themselves begin to fly apart as their stars disperse into the expanding void. Then solar systems destabilize, planets drift away from their stars. As the end approaches, even stars and planets themselves would be torn apart, and then molecules and atoms. In the last fractions of a second, the tidal forces of expansion would become essentially infinite, shredding the very subatomic particles. This hypothetical final calamity is called the Big Rip. It would be a universe ending in a kind of ever-accelerating explosion, where every bond, gravitational, electromagnetic, even nuclear, is overcome by the expansion of space. One moment, you might have galaxies. Moments later, only individual atoms. Finally, nothing at all but a thin, featureless energy as space rips itself apart. It's a highly speculative scenario. Current data do not favor such extreme dark energy behavior, but it serves to illustrate the dramatic ways our universe's story could conclude under different rules. On the other hand, what if dark energy were to weaken over time or even reverse sign? Or what if the universe had contained so much matter that gravity could eventually overwhelm expansion? In those cases, the expansion might slow down, stop, and ultimately reverse. Distant galaxies that are now receding would one day halt and begin to come closer again. This is the Big Crunch scenario, the opposite of the Big Bang. In a universe headed for a big crunch, observers in the far future might see the expansion first slow to a crawl. Distant galaxies that once sped away would linger at the edge of visibility. Then, gradually, they would start to approach, their light shifting from red back to blue. The cosmos would begin to shrink. Over billions of years, separated clusters of galaxies would converge. Previously unreachable galaxies would become visible again as they rush inward. The cosmic microwave background temperature, which had been dropping, would begin to rise as the universe contracts and heats up. Eventually, the night sky would no longer be dark, but aglow, first dotted with an increasing number of bright galaxies coming together, then suffused with the glow of a background fire as intergalactic gas is compressed and reheated. In the final epoch, the entire sky might blaze like the surface of a star, white hot, as galaxies merge into a single, incandescent mass. Finally, all matter and energy would crash together in an ultra-dense state, perhaps a mirror image of the Big Bang. Some have imagined that such a collapse could bounce, an implosion leading to a new explosion, a Big Bang after the Big Crunch, giving birth to a new universe. This Big Bounce idea suggests a cyclic cosmos without beginning or end, eternally reborn. However, given what we observe, particularly the presence of dark energy, a Big Crunch seems very unlikely for our universe. The balance of evidence indicates that we are headed toward eternal expansion, either the Big Freeze or Big Rip, with Big Freeze considered far more plausible under current data. Nevertheless, thinking about these scenarios reminds us that our universe's story might have multiple chapters, and perhaps even an epilogue beyond our own cosmos. As we ponder the fate and origin of our universe, we naturally wonder, is our universe the only one, or is it just one bubble in a vast frothing sea of universes? Modern theories in cosmology and physics have opened the door to the idea of a multiverse, the possibility that our universe is not alone, but part of a far larger system of universes. The existence of dark energy and the precise balance of physical constants in our universe have led some to wonder if our cosmos is just one of many, its properties one random draw among myriad universes. In a multiverse, what we call fine-tuned constants of nature, like the strength of gravity or the charge of the electron, might vary from one universe to another. We find ourselves in one that permits galaxies and life simply because those that don't would be sterile and uninhabited, with no observers to notice them. One compelling multiverse idea arises from the theory of eternal inflation, a variant of the inflationary scenario we discussed earlier. In eternal inflation, the rapid expansion of space didn't end everywhere at once. While inflation stopped in our region, allowing particles and galaxies to form, other regions of space might still be inflating, or might have ended their inflation at different times, each giving rise to its own bubble universe. Our universe, then, would be one such bubble among countless others, expanding within a larger inflating space-time. Each bubble could have its own distinct laws or constants. Some might be barren, with no matter, or with physics hostile to complexity. Others might be roughly similar to ours. Perhaps others are wildly different with more dimensions or different fundamental forces. We cannot directly see these other bubble universes because they would lie beyond our cosmic horizon and indeed beyond any space-time connection with us. But they are a natural extrapolation of inflation theory. These other universes could be as real as our own, each constituting its own reality bubble. The multiverse concept comes in different flavors. The Level 1 multiverse essentially says that if space is infinite and uniformly filled with matter, then far beyond our observable horizon, there could be regions identical to ours,
or slightly different, or vastly different, simply by random chance arrangements of matter. In an infinite universe, every possible configuration of particles, every possible history, would occur somewhere. Our observable universe would be just one patch of an infinitely vast quilt. The Level 2 multiverse corresponds to the eternal inflation scenario, bubble universes. Each bubble might have different physical constants or particle types, because the process of symmetry breaking in physics could end up differently in each one. One bubble might have a stronger electromagnetic force. Another might have a neutron a bit heavier, preventing stars from working. We find ourselves in a bubble that is congenial to complexity, because only such bubbles can produce observers. Another intriguing idea is the Level 3 multiverse, which arises from quantum mechanics, the many worlds interpretation. In quantum theory, every event that has multiple possible outcomes, like a particle decaying or not decaying, is sometimes thought of as splitting reality into multiple branches. According to this interpretation, all possible outcomes actually occur, each in its own branch of the wave function of the universe. So in one quantum branch, universe, the cat is alive. In another, it is dead, to invoke the famous Schrödinger's cat thought experiment. These parallel universes are usually thought to be non-communicating, existing in a superposed mathematical state, rather than separate inflating bubbles. But some argue they are just as real as our own. In effect, this would mean that with every quantum event, the universe, at least at the level of quantum information, splits into multiple histories, creating an ever-branching tree of parallel realities. If true, the number of universes would be mind-bogglingly large and constantly increasing. There is even a conjectured Level 4 multiverse, the ultimate ensemble, which posits that all universes that can be described by consistent mathematical structures exist in some sense. In this view, mathematics and reality are one and the same. Any self-consistent set of physical laws, any mathematical model, corresponds to an actual universe somewhere. This is a philosophical speculation more than a scientific theory, but it underscores how far the multiverse idea can be taken. So, could it be that what we call everything, our observable cosmos, is but a drop in a much grander ocean of existence? It's possible. At present, the multiverse remains a theoretical idea. We have no direct evidence of other universes, and some argue we never could, by definition. Yet the concept finds footing in serious science because it can arise naturally from models like inflation, and because it offers answers to questions like why our universe has the properties it does. They might be random picks from a larger distribution. If the multiverse is real, then the totality of existence is even grander than the universe we've been discussing. It means there could be countless other Big Bangs, countless other expansions, perhaps countless other versions of you and me, or perhaps realities utterly without analogy to anything we know. It is a speculative, almost metaphysical extension of our theories, one that reminds us that as vast as the universe is, there could be more, much more, beyond it. No matter how many universes exist, we know that we can only directly explore our own, and it has plenty of mystery to keep us occupied. One such mystery is deeply connected to our everyday experience, the nature of time. Time flows ever forward, carrying us from moment to moment. We remember the past and anticipate the future, but we never experience events in reverse. This one-way direction of time, from past to future, is called the arrow of time. Why does time have an arrow? The answer, as far as physics can tell, lies in entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics states that in an isolated system, entropy tends to increase or, at best, stay the same. It never decreases spontaneously. This law gives a direction to processes. Things go from ordered to disordered, not the other way around. An egg breaks and scrambles, but a scrambled egg
does not unbreak itself into a whole egg. A drop of ink disperses in water, but the ink won't gather back into a concentrated drop on its own. These processes are not forbidden by any fundamental microscopic law. Newton's and Schrödinger's equations work the same forward and backward in time, but they are overwhelmingly unlikely to happen in reverse, because that would require a decrease in entropy. The arrow of time in our universe is fundamentally linked to the initial conditions of the cosmos. The universe began in an extraordinarily low entropy state. This might sound strange because the early universe was a hot, dense plasma which seems very disordered, but in fact, it was extremely uniform and simple, free of complex structures, making its entropy lower than it could have been. It's as if all the matter and energy were evenly spread out and gravitationally unclustered, a very ordered configuration compared to what could be. Because the universe started with such low entropy, there was essentially nowhere to go but toward higher entropy. As the universe expanded and cooled, entropy increased, gradients smoothed out, structures formed even as overall disorder grew. For example, the formation of stars and galaxies increases local order, but overall entropy still rises due to the production of lots of waste heat and the gravitational settling that releases energy. The arrow of time is a manifestation of this rise of entropy. We perceive time flowing forward because that is the direction of increasing entropy. If you were to film a glass shattering and play it backwards, you'd see entropy decreasing and immediately intuit that time is reversed in the film. In the real universe, we do not see such things. One might ask, why was the entropy of the early universe so low to begin with? This remains one of the deep, unanswered questions in cosmology. Some suggest it might be a boundary condition of our universe, perhaps set by a prior state or by the laws of quantum gravity. Others propose that if there are multiple universes or cycles, we naturally find ourselves in one that started in a low entropy state, because only such a universe can develop the complexity needed for observers. Regardless, that low entropy beginning is what allowed an arrow of time to emerge. From it flowed the entire history of structure and complexity. Stars shine, increasing entropy by radiating heat. Life grows and metabolizes, increasing entropy in surroundings even as it creates local order. And eventually stars die and things run down. If we project trillions upon trillions of years forward, in the heat-death scenario, entropy will near a maximum. The arrow of time will effectively fade, not because time has reversed, but because almost nothing changes anymore. There are no organized processes left to distinguish a forward direction. In the far, far future of a big freeze, the universe might reach a state of near equilibrium where, without gradients or differences, the concept of before and after loses much of its meaning. Time and entropy tie together the grand cosmic and the intimate personal. The increase of entropy sets the thermodynamic arrow that makes memory possible. We remember lower entropy past states. It is why we grow older and not younger. It's the reason we can't unmix cream from coffee or unburn a piece of paper. It's fascinating that this everyday irreversibility is rooted in the initial conditions of the entire universe. We've journeyed from the enormous clusters of galaxies to the minute atoms and particles, but we haven't yet delved into the truly fundamental fabric underlying reality, the quantum realm. On the smallest scales, the world behaves in ways that defy our classical intuitions. In the quantum realm, particles are also waves, and everything is described by a fuzzy haze of probabilities rather than definite certainties. Take an electron. In an atom or in transit, it doesn't have a single precise location. Rather, it exists as a cloud of probability, a smeared out wave of potential positions. Only when we interact with it, measure it, does the electron seem to choose a location or state. This is the bizarre phenomenon of wave function collapse, in interpretations where collapse is a thing. Before observation, Schrödinger's cat is both alive and dead in a quantum sense. Before measurement, the electron has many possible positions. For example, If we shoot electrons at a screen through two narrow slits, something astonishing happens. The electrons, one by one, form an interference pattern on the detection screen, alternating bands as if they were waves that passed through both slits and interfered with themselves. This happens even if we fire them one at a time. It's as though each electron goes through both slits as a spread-out wave. However, if we set up a detector to observe which slit the electron actually goes through, trying to catch it in the act and force it to be a particle going through one path, the interference pattern disappears. Now the electrons behave like little bullets, going through one slit or the other, and no interference fringes form, just two piles behind the slits. The mere act of observation changes the outcome at the quantum level. It's as if nature allows the electron to explore many possibilities, wave behavior, until we insist on knowing which one happened, at which point nature chooses and the wave of possibility collapses into a single result. Empty space itself is not truly empty in the quantum sense. Even in a perfect vacuum, quantum fields are continuously fluctuating. Particle-antiparticle pairs momentarily pop into existence and then annihilate so quickly and so spontaneously that we can barely infer their presence. They leave subtle effects on energy levels and forces. These quantum fluctuations are not just theoretical quirks, they had cosmic consequences. During inflation, those tiny fluctuations in density and energy were stretched out to macroscopic scales. Regions that were ever so slightly more dense or less dense than others became the seeds for all large-scale structure. The spots in the cosmic microwave background that are a bit warmer or cooler, denser or less dense, trace back to these quantum wiggles. It is a breathtaking linkage. The reason galaxies exist where they do is partly because of random subatomic jitter in the universe's earliest moments. The entire cosmic web is essentially amplified quantum noise. Quantum physics underpins nearly everything in our daily experience, even though we don't notice its strangeness on large scales. The atoms in our bodies are held together by electron wave functions and quantum bonds. The sun shines because quantum tunneling allows protons to overcome their electrostatic repulsion and fuse into helium. Without quantum tunneling, the sun's core wouldn't ignite as easily. Computers and modern technology rely on quantum mechanics, semiconductors, lasers. In a sense, the solidity of a rock, the behavior of a chemical reaction, the colors of the rainbow, all trace back to quantum rules. We live in a quantum universe, though its oddness becomes apparent only when we look at small scales or specific conditions. There is also the deep mystery of quantum measurement and reality. Does the wave function collapse when observed? Does the universe split into branches for each outcome, the many worlds idea? No one knows for sure which interpretation of quantum mechanics is correct, or if there's a deeper theory that will resolve these questions. What we do know is that quantum mechanics is astoundingly successful in predicting outcomes. It has been tested to high precision. Reality, at its foundation, is governed by probability waves and uncertainty. It's almost as if nature, at a fundamental level, decides events by a kind of controlled randomness within strict statistical rules. Our voyage has taken us from the beginning of time to the structure of space, from the largest assemblies of galaxies to the subatomic flickers of the vacuum. Along the way, we encountered phenomena that are poetic in their grandeur and scientific in their detail. An afterglow from creation itself still shining to us, invisible matter holding galaxies in its gravitational embrace, a mysterious energy pulling the cosmos apart, and quantum whispers setting the stage for galaxies. Let's return for a moment to that ancient light we freed at recombination, the cosmic microwave background, CMB. After traveling for 13.8 billion years, it reaches Earth as a faint, cold glow in all directions, a few photons per cubic centimeter. In 1965, two engineers, Arno Penzias and Robert Wilson, were using a big horn antenna in New Jersey. trying to eliminate all sources of noise from their radio measurements. They kept encountering a persistent hiss, uniform across the sky, day and night. At first, they thought it might be due to urban interference, or pigeon droppings in their antenna, or instrument malfunction. But none of those explained it. Meanwhile, a group of physicists at Princeton, Dicker, Peebles, et al., had been looking for exactly such a signal. The predicted relic radiation from the hot early universe, which years earlier, scientists like George Gamow had calculated should by now be just a few degrees above absolute zero. Penzias and Wilson had stumbled upon the very signal that those theorists were seeking. It was soon confirmed that this microwave hiss came from all directions uniformly and had a blackbody spectrum of about 2.7 Kelvin, just what the Big Bang model predicted. The cosmic microwave background was the long-predicted afterglow from the hot young universe, now cooled to a whisper. When we map the CMB across the sky, as satellites like COBE in 1989, WMAP in the 2000s, and Planck in 2013 have done with increasing precision, we find it is almost the same in every direction, extremely uniform to about 1 part in 100,000. It's as if the entire sky were painted with one color of incredible smoothness, with only the faintest speckles. Those speckles, the tiny temperature anisotropies, carry a wealth of information. They are the imprints of the primordial sound waves and density ripples in the early universe. The pattern of spots tells us the universe's age, composition, and geometry. By carefully analyzing the CMB, scientists have confirmed the age of the universe, how 13.8 billion years, determined that space is flat to within a tiny margin of error, and measured the ratios of normal matter, and dark energy that we mentioned. The CMB is like a baby picture of the universe, taken when it was only 380,000 years old. In that baby picture, we can already see the slight non-uniformities that eventually grew into clusters of galaxies. It's astonishing that we can observe this. When you tune an old television between channels and see static, a small fraction of that static is actually CMB photons, literally relics from the Big Bang hitting your TV's antenna. The CMB also provides evidence that ties together many threads of our story. It confirms the Big Bang. A static universe would not have such a background. It supports inflation. The uniformity and specific patterns match inflationary predictions. And it informs the dark matter models. The CMB pattern is sensitive to the amount of invisible mass. It is a Rosetta Stone for cosmology, decoded through careful, rigorous science. And yet, when one simply gazes at the visualizations of the CMB, with its gentle swirls of red and blue, indicating tiny temperature fluctuations, one can't help but feel a sense of wonder. This mottled oval image, often shown in textbooks and documentaries, is the imprint of the primordial cosmos on the sky, the oldest light we will ever see, a light that has traveled for almost the entire history of the universe to reach us. Within this vast cosmic unfolding, on at least one small planet, the expansion and cooling of the universe eventually led to something new: life and consciousness. The atoms forged in stars and scattered by supernovae became the raw material for new star systems. About 4.6 billion years ago, one particular cloud of gas and dust, already enriched by previous generations of stars, collapsed to form our Sun and its family of planets. The third planet from this sun had the right conditions for a remarkable chemistry. In its early oceans and coastal environments, a rich molecular broth swirled. On this young Earth, a complex chemistry brewed in warm ponds, in tidal pools, and around underwater hydrothermal vents. Complex molecules formed in the warm, wet cradles, perhaps sparked by lightning in the atmosphere or by geothermal energy in the crust. Perhaps in sunlit shallow pools, left to evaporate on volcanic shores, or in the mineral-rich hot springs on the ocean floor. Simple chemistry crossed the threshold to self-replication. At some point, simple self-copying molecules emerged. This was the origin of life, around 4 billion years ago. From those humble beginnings of primitive microbes, life evolved in complexity
and diversity shaped by mutation, competition, and time. Tiny cells coalesced into more complex cells, which eventually formed multicellular colonies. By around 540 million years ago, the Cambrian explosion filled the seas with an astonishing variety of creatures. Life took hold on land. Plants and fungi colonized the continents, followed by insects and amphibians, then reptiles and dinosaurs. Each living organism was, and is, a little chemical machine, drawing energy from the environment to maintain its internal order, a local reversal of entropy paid for by increasing entropy in its surroundings. In this way, life is a kind of cosmic rebellion against the trend toward disorder, though only a temporary and localized one. Through life, the universe explored an entirely new realm of complexity. After dinosaurs were wiped out 66 million years ago by an asteroid and other factors, mammals rose to prominence. Some primates in Africa, a few million years ago, left the trees for the savanna. They grew bipedal and clever. They made tools and learned to cooperate in groups. By about 300,000 years ago, anatomically modern humans had appeared. With the emergence of Homo sapiens, the universe began to be aware of itself in an unprecedented way. We gazed at the stars with curiosity and imagination. Over thousands of years, we developed language, culture, mythologies about the cosmos. We harnessed fire, energy for entropy consumption. We built shelters. We eventually tilled fields and founded cities. We looked up and saw patterns in the sky, crafting constellations and calendars. Human curiosity pushed us to ask not just how to survive, but why we are here, what the stars are, what the sun is, and how it all began. Fast forward to the modern era. In just the past few centuries, we have, through the scientific method, unraveled many cosmic mysteries. We discovered that those points of light in the night sky are other suns, and some of those suns host planets of their own. We've confirmed thousands of exoplanets and infer that the galaxy holds billions more. We found that our sun is just one star among hundreds of billions in the spiral galaxy we call the Milky Way, and that our galaxy is just one of trillions in the observable universe. We've begun to understand the forces and particles that govern nature. We've peered back in time with powerful telescopes to see galaxies in their infancy, and we've peered into the atom to unlock the secrets of quantum physics. Life, at least here, evolved to consciousness that can contemplate the universe. That is a profoundly poetic fact. We are made of dead stars, and those very ashes have somehow become alive and able to wonder about their origins. The universe spent billions of years evolving us, and through our eyes, it now sees itself. We are a way for the cosmos to know itself, Carl Sagan famously said, encapsulating this truth. Our self-awareness makes the universe not only a physical phenomenon, but also an experience. Through our literature, art, and science, the cosmos has gained the ability to reflect upon itself, to study its own laws, to admire its own beauty. Are we alone in this astounding capability? Perhaps not. The universe is so vast that it seems improbable that Earth would be the only cradle of life. Perhaps in some warm pond on an exoplanet under a distant sun, chemistry has given rise to biology. Perhaps on a moon orbiting a gas giant, beneath an icy crust, alien microbes flourish near thermal vents. Maybe on some planet in the habitable zone of another galaxy, intelligent creatures build their own tools and look up at their sky with questions. As of now, we don't have evidence of life beyond Earth, but the possibility stirs our imagination. Whether life is common or exceedingly rare, the fact remains that life here has transformed a part of the cosmos into something self-aware. And so here we find ourselves, clever, self-aware creatures built of cosmic dust, living on a minor planet, orbiting an ordinary star in a typical galaxy, yet able to contemplate the entirety of existence. Our physical insignificance is undeniable. We are infinitesimal compared to the breadth of the cosmos. Our entire world is just a tiny mote of dust in a cosmic ocean, a pale blue dot adrift among countless stars. But our ability to understand and appreciate the cosmos gives us a significance of a different kind. We might be rare, perhaps the only intelligent beings for parsecs around, or maybe one of only a few in our galaxy. Maybe life teems in the universe, or maybe it is exceedingly scarce. Either way, in our corner of space and time, we are the only known eyes and minds observing the grand cosmic drama. Through us, the universe has become aware of itself. Through our scientific instruments, the universe maps its own structure. Through our poetry and art, the universe speaks of its own majesty. There is something profoundly meaningful about this, even if one views it in a purely secular, scientific way. The cosmos has given rise to beings who can know the cosmos. We have inherited the fiery hearts of ancient stars in the iron of our blood, the calcium of exploded supernovae in our bones, and the carbon and oxygen from countless stellar furnaces in every organic molecule of our bodies. We are literally children of the stars, made of stardust. And those children can now, like grown progeny, look back and study their parents, the stars, and grandparents, the galaxies, the Big Bang. This unity of origins gives us a connection to everything. We are not separate from the universe. We are portions of it, inextricably linked. The laws of physics that formed a galaxy also form the neurons in our brain that fire when we gaze at a galaxy. With knowledge, however, comes the humbling realization of how much we don't know. Our journey through cosmology answers many questions, but raises others. Why is there something rather than nothing? Did time begin with the Big Bang, or is there a multiverse with different realms beyond ours? What is the true nature of space and time on the smallest scales? Are they quantized into discrete bits, as some theories like quantum gravity suggest? We don't yet have a fully unified theory of quantum mechanics and gravity. Thus, the exact first moments of the Big Bang, the Planck time, and what happened before inflation remain mysterious. We still do not know what dark matter is, despite it making up most of the matter in the universe. We still do not know why an early hyperinflation happened, or if it's even the final answer to the early universe's smoothness and flatness. We aren't sure if dark energy is truly constant or has subtle variations, and the nature of dark energy, why vacuum has the energy it does, is deeply perplexing. In fact, theoretical physics calculations of vacuum energy overshoot observations by an outrageous factor, a major puzzle. We do not know if life is a common cosmic phenomenon, or an extremely lucky fluke confined to Earth. We have not yet detected signals from other civilizations, though projects like SETI are listening. We do not know the fate of humanity, whether we will spread to the stars or remain bound to our lovely, pale blue dot. In short, we still float on a sea of mystery, with islands of knowledge gained so far. Standing at this precipice of knowledge and mystery, one cannot help but feel a profound awe. The universe is ancient and vast beyond comprehension, yet here we are, small creatures with curious minds, capable of tracing its story from the primal fireball to the present, and even forecasting its possible futures. That story, from the simplicity of the early fireball to the complexity of a living world, is both humbling and inspiring. The cosmos is breathtaking, not just in scale, but in the way it has produced patterns and coherences. The periodic table of elements forged in stars, the spiral patterns of galaxies, the double helix patterns of DNA that allowed creatures like us to emerge. There is a deep harmony in how the same physical laws apply across all scales. The nuclear reactions blazing in the core of a distant star obey the same physics as the glow of your reading lamp. The gravity that makes a planet orbit the sun is the same gravity that makes galaxies dance around one another in clusters. Mathematics, abstract patterns of logic, proves to be an incredibly effective language to describe these laws, suggesting a wondrous connection between the human mind and the workings of the universe. It's as if the universe has a hidden symmetry or order,
that we can glimpse through mathematics and science. Our journey of understanding is far from over. Each new discovery in astronomy or physics tends to open new questions. When we discovered the expansion of the universe, we were led to ask about the beginning, Big Bang, and the ultimate fate. When we found the cosmic microwave background, we were led to the idea of inflation. When we observed unexpected galaxy rotations, we hypothesized dark matter. When we measured distant supernovae, we stumbled upon dark energy. Every time we peel back a layer of reality, there is another layer waiting, sometimes with stranger questions. This is the beauty of science and exploration. A continuous unfolding story, each chapter building on the last, but the book seemingly without end. Picture the cosmic timeline as a grand narrative, a story that begins with nearly featureless energy and evolves into intricate worlds and beings. It's a story that spans 13.8 billion years and perhaps will span trillions more. To grasp our place in this timeline, imagine compressing the entire history of the universe into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. By early February, the first stars ignite. By mid-March, galaxies are forming. The Milky Way might form around May. Our Sun and Earth appear roughly in early September on this cosmic calendar. Life arises on Earth by late September. Complex multicellular life proliferates in November. Dinosaurs roam the Earth on December 25th, Christmas Day, and go extinct on December 30th. Modern humans emerge only in the final hour of New Year's Eve, and all of recorded human history flashes by in the last seconds before midnight. In those final seconds, we develop agriculture, build the pyramids, invent the telescope, land on the moon, and contemplate the Big Bang. When the clock strikes midnight to herald a new cosmic year, perhaps that represents some distant future state we've yet to comprehend. This cosmic calendar shows just how young we are. Human civilization is an eye blink in cosmic time, and even the Earth is a relatively late chapter in the story. We arrived at the tail end of the year, so to speak, but armed with curiosity and intellect, we busied ourselves in those last seconds learning about all that came in the months before us. Now we, ephemeral yet mindful, look to the future. We wonder what's next for the universe and what's next for us. Barring extraordinary intervention, the universe will continue to expand and evolve according to the physical processes we have discussed. As for humanity, we too are subject to cosmic forces, but have some say in our destiny if we are wise. We may spread to other planets, carrying our legacy of curiosity with us beyond Earth, ensuring that life and consciousness have a longer future than our single planet's fate. We may find ways to harness new energy sources or manipulate space-time, ideas once in the realm of science fiction, but who knows what knowledge awaits in the coming millennia. Or we may struggle and someday perish, becoming a brief spark that faded out. But even if our particular lineage ends, perhaps other intelligences elsewhere will carry on, or new intelligences might evolve from what we leave behind, intelligent machines, or new species. The desire to know and to wonder might itself be as resilient as life. From the standpoint of the universe, meaning is not something handed down from the stars. It is something we create. We infuse the cosmos with meaning by contemplating it. A galaxy 100 million light-years away has no idea of its grandeur, but we know, and in knowing and seeing beauty in it, we give it meaning, at least to us. In a way, the cold equations of physics blossomed into the warmth of human experience and inquiry. The universe is often described as a cold, uncaring place, and physically it is vast and mostly inhospitable. But through us, it cares about itself, in the sense that we care and we are part of the universe. This connection may be philosophically subtle, but it is emotionally powerful. Our exploration is ongoing. Even now, new telescopes like the James Webb Space Telescope peer into the distant past,
seeing galaxies forming just a few 100 million years after the Big Bang, giving us new data points in the cosmic saga. Particle accelerators, like the Large Hadron Collider, probe higher energies, trying to recreate conditions just after the Big Bang, searching for clues of new physics, perhaps particles that could explain dark matter or hints of extra dimensions. Experiments in deep mines attempt to catch a glimpse of dark matter particles zipping through Earth. Space probes explore planets and moons, looking for signs of past or present life beyond Earth. Mars's ancient riverbeds, the subsurface ocean of Europa, the methane seas of Titan. We are, in a sense, turning over every stone we can in this universe to piece together the puzzle of reality. Standing on the precipice of all this knowledge and mystery, we feel both incredibly small and incredibly enriched. The night sky no longer just offers twinkling points of light. It is a time machine, showing us distant galaxies as they were eons ago and connecting us to the moment of creation. The ground beneath us is not just dirt, it's ancient cosmic debris, a mix of elements made in star cores, arranged by geological and evolutionary processes into our immediate environment. We, the curious specks of the universe, will keep lighting candles in the cosmic dark, striving to illuminate more of that everything, even as it continually surprises us. The quest goes on, and the wonder deepens. To be alive as a human at this moment, to have consciousness, to have the accumulated knowledge of generations at our fingertips, and the ability to extend that knowledge, is a precious, fleeting gift. Through our minds, the universe has awakened to a sense of itself, however partial. We have the privilege of witnessing this vast tapestry and the responsibility of carrying that knowledge forward. In the end, the story of the universe is not just a tale of matter and energy moving heedlessly. It is also a human story, a story of awareness and curiosity, finding a foothold in a vast cosmos. We began this journey meditating on the concept of everything. Now, at journey's end, we realize that perhaps we have only scratched the surface of everything. We close with more questions than we started, but also with a deeper reverence for existence. We sense that the strangeness and wonder of the universe will never end, no matter how much we discover. As long as there are beings curious enough to look up and ask questions, the cosmos will continue to inspire. In its darkness and its light, its simplicity and its complexity, its silence and its stories, the universe offers an endless well of awe. It is a beauty we could pursue forever and never exhaust. Take a gentle breath without end. Feel the air quietly enter and leave your lungs. For a moment, nothing exists but this tiny act, a single breath in the dark. You can hear your heart beating, slow and steady. You are in the smallest place imaginable, the space within yourself. A thought flickers across your mind and vanishes. In this hushed, intimate moment, the entire cosmos feels condensed into the rise and fall of your chest. All the rushing world around you has paused. Here is peace, a silent beginning. From that silence, your awareness begins to expand. It's as if your mind's eye opens and starts to float upward. You drift beyond your body, still curled quiet and warm, and rise softly above it. You sense the room around you, the gentle darkness behind closed eyelids, the floor beneath you, the faint hum of life in the distance. Your breath remains slow, but now you imagine floating higher, passing effortlessly through the ceiling, above the rooftop, above the sleeping earth. The cool night air surrounds you. You can't feel the air, but you know it's there, a thin blanket of atmosphere enveloping everything you've ever known. Rising higher still, you watch the ground fall away. The shapes of houses and trees blur into a dark tapestry. City lights glow in quiet patterns on the land. Further up, those patterns shrink to nothing. Now beneath you is a vast expanse of nighttime earth, silvery moonlight on clouds, a soft halo at the horizon where day is about to break. You are so high that dawn and night share the sky.
Above you, the heavens open, countless stars, crisp and bright, scattered across a sea of black. The Milky Way arcs overhead as a faint band of light. For a moment, you hover there, balanced between Earth and space. The world you know is a curved, glowing jewel below, and the universe an infinite mystery above. With a silent urging, you continue upward. The last wisps of atmosphere fade away. The sky goes from midnight blue to pure black. You have slipped free of Earth's cradle and entered the cosmic ocean. Below, the Earth is fully visible now, a luminous blue sphere swirled with white clouds, glowing against the dark. Our home. You notice how thin the layer of atmosphere is, just a fragile blue haze along the curved edge. All of life, all of history, contained in that delicate film around the planet. From here, Earth is serene and small, a pale blue dot suspended in an endless void. You feel a quiet awe, realizing that everything you've ever experienced is on that tiny, bright world drifting below you. You drift farther out. Continents and oceans merge into a single marble of blue, white, green, and brown. The bright sun now peaks around the Earth's edge, igniting a halo of light. For a moment, Earth is just a silhouette crowned by dawn. Moving into space's shadow, you see night swallowing half the globe, city lights twinkling on the dark side in silent testimony to humanity. Then even those lights fade. Earth becomes a smaller and smaller circle, shrinking as you float away. Soon, it's just a shimmering dot, like a star. That is home, that tiny point of light, alone in the cosmic dark. Passing the moon's orbit, you look back and see the Earth and moon together, one shining, one softly grey, dancing in eternal circles. The moon, pockmarked and ancient, glows faintly with reflected sunlight. For an instant, you imagine standing on the airless lunar plain, looking up at a blue orb in a black sky. How lovely Earth must appear from there, hanging in space, glowing with life. The thought fades as you journey onward, leaving the moon far behind. The Earth and moon now blend into a single pale star, falling into the background of countless other stars. You carry on, outward and outward, into the deep. The sun looms ahead, no longer a comforting daytime sunbeam, but a blazing white furnace suspended against the void. You feel no heat out here, but you see its brilliant light, a beacon in the darkness. You drift past an inner planet. It's Mercury, a barren, scorched rock, mottled with craters, racing around the sun. Then Venus, cloaked in thick, toxic clouds, gleaming like a pearl. The warmth of the sun diminishes as you go farther, and now the blue-green jewel of Earth is behind you, third planet from the sun, already lost in the sun's glare. Ahead, the rusty world of Mars appears, with its deserts and canyons and faint whiffs of bygone hopes. You glide beyond Mars's orbit, leaving the inner solar system. A cold emptiness envelops you as the sunlight grows weaker, turning golden, then pale. Floating in silence, you pass through the asteroid belt, a vast field of rocks and ice chunks orbiting the sun. They are spread out like dust in a sunbeam. You see only a few asteroids tumble by, ancient and silent. Farther still, the giant planets await. Jupiter materializes, enormous and banded, its great red spot swirling. A centuries-old storm, big enough to swallow Earth. 4 bright moons circle it, miniature worlds in their own right. Volcanic Io, icy Europa, massive Ganymede, cratered Callisto. They glide around Jupiter like a miniature solar system, lit by the distant sun. Next comes Saturn, Lord of the Rings, its golden globe encircled by wide, delicate bands of ice. You marvel at the sheer elegance of those rings, like cosmic artwork carved from light. Titan, Saturn's hazy moon, and a fleet of smaller moons orbit nearby, tiny sparkles moving through Saturn's complex grace. You drift faster now, as if eager to see more. Uranus appears, tipped on its side, a pale cyan orb with faint rings and moons dotting around its tilted equator. Neptune follows, deep blue and mysterious, with winds screaming silently across its methane clouds. Far from the sun now, darkness deepens. The sunlight is just a feeble glimmer, like late twilight on Earth. You pass the orbits of the most distant known worlds and enter the outer realm of the solar system. Here, far beyond Neptune, a trillion frozen comets form a tenuous halo called the Oort cloud. These are the ancestral wanderers that sometimes fall sunward and become the glowing comets in our sky. You drift through this cloud of potential, countless icy bodies spread over light years of space, so thinly that you hardly notice when one slips by, a silent snowball waiting for a chance to visit the inner sun. Finally, you reach the edge of the sun's domain. Behind you, the sun is now just another bright star, its family of planets too small to see. In 1977, humanity sent a messenger this far, a Voyager, now over 40 years into its endless journey. It has long crossed the border where the solar wind's breath yields to the breeze of interstellar space. You have followed it into the truly unknown, the space between stars. Here, there is almost nothing, just a few stray atoms per cubic meter, a dusting of cosmic rays, a memory of starlight. The darkness is profound and quiet. Before you, the stars stretch out in every direction. The nearest star to our Sun, Proxima Centauri, lies over 4 light years away. So distant that even at the speed of light, the fastest speed there is, it takes over 4 years for a beam to travel from our Sun to that star. At your supernatural pace, distance means little, but you recall what this emptiness signifies. The gap between stars is vast beyond imagining. If you were traveling in a ship, moving as fast as any human ever has, it would take tens of thousands of years to reach even the nearest neighboring star. Space is mostly emptiness. You are grateful that as a thought, a consciousness drifting free, you are unbound by such limits. You can roam the interstellar gulf freely, carried only by curiosity. A dim, reddish star comes into view. Proxima, a faint red dwarf, companion to the brighter Alpha Centauri double star system. Perhaps a few small planets cling to it. One, we know, is in a temperate zone, but it is far too faint and distant to reveal itself to our naked eyes. You drift past it swiftly, moving ever outward, picking up speed now. The stars around you begin to form subtle patterns, a hint of structure in the sprinkling of lights. They are no longer random points. You start to notice a concentration of stars in one broad band, the plane of the Milky Way galaxy. From inside, the Milky Way is that cloudy band across our sky. But as you rise above the galactic plane, you begin to comprehend its true form. Pulling farther out, you see our galaxy in full. Behold the Milky Way, a great spiral galaxy, majestic and sprawling, rotating slowly in space. It's like a giant, flat disk of stars with a bright central bulge. Huge, wispy spiral arms unwind from the center, like the arms of a graceful octopus, each arm glittering with millions of stars. Here and there, dark lanes of dust weave through the starlight, obscuring parts of the arms. The disk of the galaxy is over 100,000 light-years across, so wide that even light itself, at its incredible speed, takes 100 millennia to cross from edge to edge. This colossal system holds perhaps 300 billion stars. Amid those, our Sun is just one modest yellow star located about halfway out from the center, in a minor spiral arm called the Orion Arm. All around the flat disk swarm countless stars, blue giants, yellow suns, red dwarfs, alongside glowing nebulae where new stars are born and old stars' remnants where they died. Your perspective drifts high above the galactic plane, giving you a view akin to a cosmic vantage point few could ever see.
The Milky Way's spiral pattern lies below you now, slowly rotating clockwise. The central bulge is bright and teeming, millions of stars densely packed near the core, orbiting an unseen monster. At the very heart of our galaxy, in that central hub, lurks a supermassive black hole. Invisible against the radiant starlight, it makes itself known through the furious orbits of stars whipping around an empty darkness. This black hole weighs millions of times more than our Sun, and its gravity is so intense that not even light can escape once drawn in. Occasionally, a star ventures too close and gets ripped apart, sending flares of X-rays out. But mostly, this dark heart quietly governs the orbits of inner stars. Time and space themselves warp around it. If you could hover just outside its event horizon, the point of no return, time would slow to a crawl for you relative to the outside universe. From far away, you'd appear frozen in place near that abyss. Such is the strange nature of gravity, foretold by Einstein. Where gravity is strongest, time runs slowest. You drift a cautious distance from this central darkness, feeling a reverent respect. In the huge panorama of the galaxy, the black hole is but a pinprick at the center, yet it affects the dance of stars around it profoundly. You leave the galactic center behind and sweep out beyond the Milky Way's disk. The galaxy's full magnificence lies before you, a glowing spiral hovering in space, its starlight diminishing at the edges into faint, tenuous streams. Surrounding the flat disk is a nearly invisible halo of mysterious dark matter, massive yet unseen, extending far beyond the visible galaxy. Though you cannot see it, this dark matter halo is there, holding the galaxy in its gravitational grip. Without it, the stars in the outskirts would fly off into space, unable to be held by the gravity of the visible matter alone. The luminous Milky Way is like a jewel embedded in an enormous, hidden cloud of dark matter that outweighs all the stars by 5 times or more. It's a strange thought. Most of the matter of our galaxy is invisible, a transparent ghost shaping the galaxy's fate. But you sense its presence as a gentle tug, a scaffold on which the galaxy is built. Now you look around and realize the Milky Way is not alone. In this vast cosmic neighborhood, it has companions, an island universe among others. Floating relatively nearby is another majestic spiral, Andromeda, our sister galaxy. Andromeda is larger than the Milky Way, a sprawling city of 1 trillion stars, 2 million light years away. It appears as a faint smudge from Earth's skies, but from here, hovering in intergalactic space, you see it face on in all its glory, spiral arms, bright core, a mirror to our own galaxy's splendor. Andromeda and the Milky Way are falling inexorably toward each other. In several billion years, far beyond any human timescale, these 2 giant galaxies will collide and merge, their stars mingling like grains of sand pouring together. Perhaps they will form a new, larger elliptical galaxy, and the night skies of whatever worlds exist then will be filled with a stunning fireworks of new star formation. But that future cosmic dance is eons away. For now, the galaxies simply drift as silent neighbors. You also notice a collection of smaller, fuzzy patches, dwarf galaxies. The Magellanic Clouds, satellite galaxies of the Milky Way, are there trailing like 2 attendants. Andromeda has its own retinue of dwarf galaxies too. Together, the Milky Way, Andromeda, and about 50 smaller galaxies form a gravitationally bound collection, the local group. You pull back further. The local group, spanning a few million light years, now appears as a tight cluster of galaxies in your view. Andromeda and the Milky Way dominate, 2 spirals swirling amid a crowd of smaller ellipticals and irregulars. As you continue to withdraw, this local group shrinks, merging into a larger pattern. You begin to see dozens, then hundreds of other galaxies glimmering in the void around. They are not uniformly spread. They too cluster in groups and chains. The local group is falling toward a much larger assembly of galaxies, a massive cluster called the Virgo cluster, home to over 1,000 galaxies. You drift in that direction, and soon a spectacular cluster fills your sight. Giant elliptical galaxies, glowing balls of billions of stars, dominate the cluster's core. One of them, M87, harbors another supermassive black hole that astronomers have imaged as a dark shadow against a ring of fire. Spiral galaxies, like whirling pinwheels, are scattered around, and numerous dwarf galaxies pepper the cluster like sparks around a bonfire. Between the galaxies, an incandescent plasma of hot gas glows in X-rays, faintly visible to your mind's eye. This intracluster gas is the sign of the cluster's deep gravity well. It's astonishing. Space can be filled with such richness in one place and such emptiness in another. Up until now, we've journeyed through space, but also, implicitly, through time. Light has a finite speed, so looking far means looking back. Pause here in the heart of the Virgo cluster, about 50 million light-years from Earth. The light reaching you from these cluster galaxies set out 50 million years ago. When that light left, on Earth the age of dinosaurs was ending. In fact, the catastrophic event that wiped them out had just occurred or was imminent. As you marvel at the galaxies, you're gazing into a time when dinosaurs still roamed our planet. Each galaxy carries its history in its light. Your journey continues outward. The Virgo cluster is part of an even larger pattern, an extended structure of galaxies known as the Virgo supercluster, or sometimes Laniakea, our local supercluster. It's a gigantic collection of galaxy groups and clusters spanning hundreds of millions of light-years. It's called Laniakea, meaning immeasurable heaven in Hawaiian, an apt name for this monumental system. From your godlike vantage, you see that galaxies are not scattered randomly. They are arranged in vast clusters, strands, and sheets. The Virgo supercluster merges into other superclusters, connected like links in a chain. There are broad patterns emerging, the large-scale structure of the cosmos. You fly further back, and now the grand design fully reveals itself. Galaxies and clusters align like cosmic architecture. Our local group and Virgo cluster are only small pieces of a much larger cosmic tapestry. Imagine a web woven in space-time, delicate yet immense. You are witnessing the cosmic web. Galaxies are the points of light on this web, strung along gossamer threads of matter that span tens, even hundreds of millions of light-years. These are the filaments of the cosmic web, the largest structures in existence, thread-like chains of galaxies and galaxy clusters. They intersect in nodes. At those nodes are massive clusters like Virgo, great cities of galaxies where filaments cross. Between the filaments lie enormous voids, empty spaces like vast black holes of nothingness, some hundreds of millions of light-years across, with hardly any galaxies inside. The galaxies outline these voids like bright frosting on a dark cake. It's as if the universe has a foamy structure. Imagine soap bubbles clinging together. The galaxies are on the surfaces of the bubbles, and the interiors of bubbles are voids where few galaxies dwell. Most of space, most of the volume of the universe, is nearly empty, the realm of these voids. The luminous galaxies we find are but a thin lattice delineating those huge cavities. You drift along one of these filaments. It's like a luminous river of galaxies flowing through a sea of dark. Each galaxy's combined starlight makes it shine like a tiny lantern, and collectively, a filament can glow faintly across hundreds of millions of light-years. Where filaments join, you encounter something even more breathtaking: galactic walls. These are immense sheets or walls of galaxies, where multiple filaments have merged to form structures spanning 1 billion light-years or more. One such wall, the Sloan Great Wall, stretches about 1.4 billion light-years end to end, so vast that a beam of light, traveling since the time dinosaurs died out, would still be only partway across. And beyond that, an even larger wall has been detected, a structure so colossal it challenges our comprehension, on the order of 10 billion light-years in length, nearly the radius of the observable universe itself. Whether it's a single coherent structure or a chance alignment, we don't fully know. But it has been nicknamed the Hercules Corona Borealis Great Wall. If real, it's a concatenation of countless galaxies and clusters, forming a spine across the cosmos. To cross it at light speed would take almost the entire age of the universe. Imagine the immensity, a wall of galaxies, billions of light-years long. Here, the cosmic web is at its grandest scale, the largest pattern in nature, a web with threads and knots spanning unimaginable distances. Hovering amidst this cosmic web, you feel a strange sensation. There is an overwhelming grandeur to it, yet an eerie stillness. The galaxies are separated by such vast gulfs that each one seems isolated, yet here you see them as pieces of one colossal structure, like single cells in the body of the universe. And underlying this web is something even more mysterious, an invisible foundation. Earlier, around the Milky Way, you sensed the presence of dark matter. Here, at the scale of the cosmic web, dark matter's role is unmistakable. These immense filaments and walls exist because dark matter's gravity drew matter into these shapes. Long ago, the universe was almost uniform, but not perfectly so. Tiny quantum fluctuations in the very early cosmos, subtle differences in density, no more than a grain more here, a grain less there, were amplified by gravity over billions of years. The regions slightly denser pulled in more matter, growing denser still, while adjacent regions gave up matter and became emptier. Through this relentless, patient process, matter collected into filaments and clusters and left behind voids. Dark matter was the key player because it does not interact with light or heat. It started clumping even when the normal matter was still a hot, ionized fog. Dark matter formed a kind of scaffolding, a hidden cosmic framework. Ordinary matter, gas and dust, then fell into the gravitational wells of that framework. Dark matter sculpted the cosmic web, and the galaxies lit up along those hidden contours. As you gaze at the cosmic web, you are actually seeing the otherwise invisible dark matter's imprint. Every galaxy is sitting in the cradle of a dark matter halo. Where you find a cluster or filament of galaxies, there lies an even larger clump of dark matter holding them together. And where you find a void, dark matter has evacuated too, leaving a truly empty expanse. Most of the mass of the universe is this dark matter, unseen yet gravitationally potent. It's humbling to realize that everything we see, all the stars and galaxies, is just the glitter on an enormous dark stage. You move through a vast void now, leaving a filament behind. Suddenly, nothing visible surrounds you, an absence of galaxies, like drifting through a huge cosmic desert. These voids are not completely empty. There may be a few stray galaxies or hydrogen atoms floating here, but compared to the bustling clusters, they are almost pure nothingness. One famous void, the Boötes void, is so large and empty that an entire cluster of galaxies the size of Virgo could fit inside it with room to spare, yet it contains almost no galaxies. If Earth were near the center of such a void, we would have discovered other galaxies only in the last century or two, because nearly all would lie beyond our visibility, until powerful telescopes were invented. In this void, the silence is palpable. It's the silence of an empty universe. No stars, no galaxies for tens of millions of light years in every direction. You might feel a chill of loneliness here, but also a sense of profound peace. This darkness is part of the universe's tapestry too. Without voids, the cosmic web would not have its striking contrast and shape. The voids are like the black backdrop that makes the galaxies shine all the brighter. After crossing the void, another filament's glow appears, and you float toward a rich intersection, a supercluster far from our own. Galaxies cluster here in the hundreds, swirling around a common center of gravity. Giant ellipticals dominate, likely formed from earlier mergers of spirals. Clusters of galaxies are entangled in a gravitational dance, slowly converging over eons.
you sense the presence of an enormous gravitational anomaly, perhaps the so-called Great Attractor, a region in the direction of the constellation Centaurus that tugs on our local supercluster itself. These massive structures tug on each other, distort the motions of galaxies on even larger scales. The cosmic web is not static. It sways and shivers in slow motion. Over billions of years, clusters merge, filaments stretch, voids expand. Ah, expand. That word reminds you, the universe itself is expanding. All around, on the largest scales, space is stretching. The galaxies recede from one another, like dots on an inflating balloon. Even as gravity pulls local structures together, the overall fabric of space expands relentlessly. You begin to notice something about the most distant galaxies in your view. Their light looks reddened. The gorgeous spiral that should have gleamed white-blue now appears tinted in soft orange-red. This is not because of dust or age, but because the very space between you and that galaxy has expanded during the light's long journey, stretching the light's wavelength. This is cosmological redshift. The farther a galaxy, the faster it recedes, and the more its outgoing light is stretched into longer, redder wavelengths. To your eyes, if you could see these distant galaxies up close, they might be brilliant with young stars, but by the time their light reaches you, perhaps tens of billions of years later, that light has been transformed into a faded echo of what it once was. It's as if the universe's expansion is a gentle, inexorable sigh, draining a bit of energy from each photon that crosses the cosmos. Expansion is not just carrying galaxies apart, it's accelerating. You recall that, a few billion years ago, the expansion of the universe started speeding up, propelled by a strange unknown force. We call it dark energy, not because it's dark like matter, but because it's mysterious. Dark energy seems to be a property of space itself, a sort of built-in pressure or tension that pushes space to expand more and more. In the past, gravity slowed the expansion as galaxies pulled on each other. But as the universe grew emptier and the galaxies got farther apart, this repulsive dark energy came to dominate, and now it drives galaxies away from each other at ever-increasing speeds. You cannot see dark energy, yet you observe its effect. The distances between far-flung galaxy clusters increase faster and faster. Over the next several billion years, this expansion will widen the voids, push clusters further apart, and isolate galaxies from each other's view. One day, in the far future, a lone astronomer in our galaxy, or its merged descendant, might look out and see only darkness beyond the local group, all other galaxies having slipped beyond the horizon of visibility. But that fate lies far ahead. For now, dark energy's influence is subtle in your journey. A slight stretching of the views, a little extra red in the far galaxy's light. Yet it's pervasive, a reminder that the cosmos is dynamic on the grandest scale. As you venture even farther, you approach the edge of the observable universe. This isn't an edge in space where you hit a wall, it's an edge in time. The farther out you go, the further back in time you peer, because that light has taken so long to reach you. At last, you arrive at a point where the first galaxies are coming into view. Tiny proto-galaxies, clumps of stars just forming. Their light is extremely faint and heavily redshifted, some of it stretched right out of the visible range into infrared and radio. These embryonic galaxies appear as small, dim patches. You are seeing them as they were over 13 billion years ago when the universe was in its infancy. These early galaxies are nothing like the grand spirals and ellipticals you saw earlier. They are smaller, more irregular, often colliding and merging. This is the epoch of galaxy formation, chaotic and creative. Massive stars in these early galaxies burn hot and blue and live short lives, detonating as supernovae that forge heavier elements for the first time. You are glimpsing the cosmic dawn, the time when the universe first began to shine with starlight after ages of darkness. One striking thing here: the space between these primordial galaxies isn't as clear as it was closer to home.
There's a haze, a fog of hydrogen gas that is only now being ionized by the brilliant newborn stars and the first quasars, galaxies with actively feeding black holes that blaze like beacons. You've entered an era shortly after the cosmic dark ages. Let's recount. After the Big Bang, once the universe cooled enough for atoms to form, the light from that early fireball could travel freely. That became the cosmic microwave background. But soon after, with no stars yet born, the universe went dark. There were no light sources, just neutral hydrogen gas pervading space. For tens of millions, then hundreds of millions of years, the universe was dark, matter pooling slowly into the first stars and galaxies. Then, perhaps around 200 million years after the beginning, the first stars ignited. Imagine that moment. For the first time since creation, darkness was pierced by starlight. Those first stars were likely gigantic, much more massive than our sun, burning hot and dying young in spectacular supernovae. They emitted intense ultraviolet light that began to re-ionize the hydrogen around them, tearing electrons off atoms and turning the gas back into plasma. As more stars and galaxies formed, this process continued like widening bubbles of clarity in a fog until the fog was fully burned away. This is the epoch you're witnessing, reionization, when the cosmic fog is lifting. It's a patchy, active period. Everywhere, infant galaxies and star clusters are switching on, lighting up pockets of space, their radiation carving out cavities in the hydrogen mist. Over a few 100 million years, these cavities merged and the haze vanished, leaving the transparent universe we know. Moving still further out and back in time, you reach a point beyond which there were no stars at all yet. Only the afterglow of the Big Bang itself fills space. You are now at the edge of the observable universe, about 13.8 billion light-years from where Earth would be, though Earth doesn't exist yet in this time frame. All around you glows a faint light, not from stars or galaxies, but a ubiquitous background. It's the color of warmth, a dim microwave glow invisible to human eyes but detectable with special instruments. This is the cosmic microwave background radiation, the oldest light in the universe that we can ever see. It's a relic from when the universe was only 380,000 years old, long before the first star, long before galaxies, when everything was an incredibly hot, dense plasma of electrons, protons, and photons. At that young age, the universe cooled just enough for electrons and protons to combine into hydrogen atoms. In an instant, the opaque fog of plasma became transparent gas, and light was free to travel. The glow we see is the afterglow of the Big Bang. Back then, it was as bright and hot as the surface of a star, around 3,000 degrees Kelvin, glowing orange-white. But in the billions of years since, the expansion of space has stretched that light to microwave lengths and cooled it to just 2.7 degrees above absolute zero. Extremely cold. Now, it is a faint, uniform whisper of microwave energy everywhere you look. If you've ever seen static on an old television tuned between channels, a fraction of that snow was caused by this primal light still arriving on Earth. Here, on the edge of the observable universe, that gentle glow is all around, like being inside a diffuse, featureless cloud of light. But it's not entirely featureless. If you look closely, you might see tiny variations, 1 part in 100,000, slight warmer and cooler spots. Those are the seeds, the very quantum fluctuations that grew into the cosmic web. In this baby picture of the universe, those warmer spots are a hair denser, the cooler a hair less dense. With time and gravity's help, the dense spots grew into galaxies and clusters. The voids grew out of the less dense spots. It's astounding to think the entire vast cosmic structure you traveled through was encoded in these faint blotches of the cosmic microwave background.
You linger here, at what feels like the limit of existence that we can perceive. This light, the microwave background,
is like a wall of light enclosing our vision. It is often called the last scattering surface because it's effectively the furthest surface from which photons could freely travel to us. Beyond it, farther back in time, the universe was opaque, a brilliant fireball of matter and energy where light was trapped. We cannot see beyond this surface with light. It's the flash of creation's afterglow. But our imagination can venture one step further. We contemplate the Big Bang itself.
Just beyond that curtain of light lies an almost unimaginable state, the universe, newborn, hot, dense, almost uniform, and extremely small. It wasn't an explosion in space, it was an explosion of space. Space and time themselves began their grand expansion here. In your mind's eye, you try to picture it. Some 13.8 billion years ago, everything, all that would become galaxies, stars, planets, people, was compressed in a volume smaller than a grain of sand, at temperatures of trillions of degrees. It is nearly impossible to fathom. But from that state, space erupted outward. The universe expanded at a phenomenal rate. There's the idea of cosmic inflation, a burst in which the universe swelled exponentially fast in a fraction of a second, smoothing and flattening space. Whether you can sense that or not, you feel that suddenly this tiny, hot universe grew and cooled. In mere minutes, it went from nothing to something the size of a grapefruit, then to the size of the solar system, and kept growing. The hot plasma formed basic atomic nuclei, hydrogen and helium mostly, in the first 3 minutes. Then expansion continued more slowly for hundreds of thousands of years as the fireball gradually dimmed and cooled. At 380,000 years, electrons joined those nuclei to form the first atoms, and the blinding opaque glow turned into the transparent universe and left behind the background light we just saw. Then darkness fell, and the stage was set for the first stars. The universe is remembering this early era in every bit of its structure. The cosmic web we saw, that intricate pattern, is like the universe recalling the quantum fluctuations and inflation that set it up. Space itself has memory, written in light and gravity. You listen to that memory, a deep silence with a subtle crackle of ancient light, like an old record playing the sound of creation. Now, as gently as it expanded, your awareness begins its journey homeward. You turn back toward the present, toward familiar shores. Slowly, you drift forward in time. You watch those primordial galaxies cluster and merge. You see the cosmic web sharpen as gravity draws filaments together and voids grow emptier. Time flows faster in your perception now. Hundreds of millions of years flicker by like moments. Galaxies take shape, merging, spinning, evolving. By a few billion years after the Big Bang, grand spiral and elliptical galaxies have formed. The universe lights up with quasars in the hearts of young galaxies, then calms as black holes settle and star formation ebbs to steadier rates. Clusters assemble, superclusters emerge. You witness the birth of our own galaxy. Tiny proto-galaxies coming together, stars forming, dying, enriching gas with heavy elements, new stars forming from that enriched material, generation upon generation. You see our Milky Way grow to maturity, developing its graceful spiral arms. In one of those arms, about 5 billion years ago, you notice a certain giant molecular cloud contracting, an unremarkable event among countless others. But to us, it's special. That cloud will become our solar system. You zoom in as this cloud spins and flattens into a disk. At the center, a protostar ignites, our infant sun. In the surrounding disk, dust grains stick together, building pebbles, then rocks, then planetesimals. Over tens of millions of years, these clump into planets. You see a small rocky planet coalesce in the warm zone third from the sun. Earth is being born, red hot and molten from collisions. Farther out, gas giants gather, and comets dance at the fringes. A Mars-sized body strikes the young Earth, a cataclysmic impact that melts it entirely and throws up debris that coalesces into our moon. Earth's turbulent youth eventually cools. Water arrives, maybe from comets or outgassed from its interior, raining down to form oceans. The sky's clear. The sun shines warmly on a water-rich world. In some tiny obscure tidal pool or deep-sea vent, around 4 billion years ago, life sparks. Simple and single-celled at first. Your cosmic journey has telescoped down to the micro now, and you find yourself marveling not at galaxies, but at cells. They grow, evolve, photosynthesizing bacteria give off oxygen, transforming the atmosphere. Eons pass. Life grows more complex. By 600 million years ago, multicellular life blooms in the seas. 400 million years ago, plants and creatures venture onto land. 250 million years ago, mighty reptiles rule the earth. 65 million years ago, a rock from space resets the stage, and tiny mammals begin their rise. The stage shifts rapidly now. Apes stand upright on the African savanna, their curious eyes now looking up at the same stars you traveled among. They wonder, they tell stories, they reach for meaning. And here you are, a descendant of those early humans, existing for just a blink in cosmic time, yet able to retrace this entire journey through imagination and science. We return fully to the present, finding ourselves hovering above that familiar blue planet, Earth, now alive with forests and oceans and cities alight in the night. We have come full circle, from the threshold of the cosmos, back to the world we call home. Gently, you descend back toward Earth. The blue dot grows larger, resolving into the globe, then into the shapes of continents and clouds. You slip into the atmosphere like a falling leaf. The ground comes up to meet you softly, and you find yourself back in the stillness of the place you began, perhaps the very room where your body sits or lies in quiet. Rejoin your body. Feel the weight of yourself against the floor or chair. Feel the cool air on your skin. Hear once more the steady rhythm of your breathing, the faint thump of your heart. You become aware that within you, mirroring the cosmos without, there is a universe of atoms and molecules. The journey outward has ended, and now the journey inward begins in reflection. You consider your hand, resting calmly. It's made of trillions of cells, each a tiny city of molecules working together, each molecule built of atoms that were forged long ago in stars. The calcium in your bones was cooked in the heart of a star that lived and died before the Earth was born. The iron flowing in your blood was formed in a supernova explosion, the death cry of a massive star, many billions of years ago, far across the galaxy. The oxygen you inhale with each breath, the carbon that forms your DNA, the nitrogen in your muscles, those elements were minted in nuclear furnaces or when stars perished in tremendous blasts. You are literally made of stardust. The universe made you from its history. You are a composite of ancient atoms, from the Big Bang's hydrogen to heavy metals from generations of stars. Even the empty space inside your atoms, and there is a lot of emptiness, as electrons swarm around comparatively tiny nuclei, echoes the vast emptiness between stars. If you could enlarge an atom to the size of a cathedral, its nucleus would be a mere grain of sand at the center, and the electrons like motes of dust buzzing at the edges. The rest is empty void. You, like the cosmos, are mostly space by volume, punctuated by tiny, energetic particles and forces. We carry within us a structure reminiscent of the cosmic structure, nucleus, like a star, with electrons, tiny planets, bound by electric forces, gravity's analog at microscopic scale. It's not a perfect analogy. Quantum reality is different. But in a poetic sense, we each contain miniature solar systems of possibility. Sitting here, you realize connection. The boundary between you and universe blurs. The cosmos is within us, as much as we are within the cosmos. Every atom in your body has existed for billions of years, cycling through various forms, born in the hearts of stars, dispersed in nebulae, incorporated into new star systems, drifting through space, eventually finding its way to Earth and into the living web of this planet, into the food you eat, the air you breathe, becoming you for a time. And when you are gone, those atoms will return to the Earth, the air, perhaps to new life, and someday, far in the future, may be launched into space again when the sun swells into a red giant and sheds its outer layers, taking your atoms back into the cosmos to rejoin the stars. We are not observers separate from this universe. We are active participants, made of its very substance and sharing its fate. Think of this. The universe has known itself through you. Over billions of years, it developed eyes to see and minds to comprehend. And those are our eyes, our minds. When you stargaze, the universe is looking back at itself. The photons that have traveled for eons enter your eyes and trigger thoughts in your brain, itself a network of atoms that were forged in stars. In a sense, the cosmos has awakened through conscious beings. We are a way for the universe to know itself, to marvel at its own grandeur. Your very awareness is as much a cosmic phenomenon as the gravity that binds galaxies or the light from the first stars. You are the cosmos, in human form, marveling at itself. Now you take another deep breath, as you did at the beginning. Feel your chest rise and fall. Feel how your body is anchored on Earth by gravity, that same gravity that holds planets in orbit and molds galaxies. There is comfort in that familiarity. The vast journey you took, from your body to the edge of the universe and back, might leave you with a sense of wonder, perhaps a touch of melancholy at our smallness, but also, hopefully, a profound sense of belonging. You belong here. The hydrogen in your body was born at the beginning of time. The calcium in your teeth, the iron in your blood, the carbon in your brain, all were brewed in ancient stars long dead, then recycled into new star systems, one of which became our solar system, our Earth, and eventually, you. You are a child of galaxies. You carry the heritage of the Big Bang and the stars in every cell. Think of all the boundaries we set between self and world, between nations, between species, and realize that on a cosmic scale, those boundaries fade. We all share the same origin. Every person, every creature, every rock and river, every atom of Earth, all were together in that incandescent singularity at the dawn of time. We all are siblings in the particle sense. When you look into another's eyes, you see the universe, just as when you look up at the Milky Way. A gentle breeze might blow outside your window. Perhaps a distant car passes. A dog barks. Normalcy surrounds you. Yet, within that normalcy is the extraordinary fact that you are part of something vast and ancient. In a quiet, almost paradoxical way, as you sit here, you contain the whole of existence because you are made of it, because you came from it, and because your mind can encompass it. The atoms in your heart and the atoms in the farthest galaxy, they are different in location but identical in nature, and they obey the same laws of physics, were born in the same cosmic processes. Slowly, you open your eyes, if they were closed. Look around the room or space you are in. It might seem ordinary, perhaps dimly lit, perhaps cluttered, perhaps serene. But notice, the light allowing you to see is a tiny slice of the electromagnetic spectrum that permeates the universe. The chair or floor supporting you is made of matter that was forged in starfire. The very air you breathe connects you to all life on Earth and to ancient stars that blew apart to seed this planet. Our journey ends where it began, with you, here and now, breathing quietly. But you carry with you the resonance of the voyage. In your mind's eye, you can still picture the spiral arms of the Milky Way, the filaments of the cosmic web, the dim glow of the cosmic microwave background. Those images are a part of you now, and whenever you feel lonely or insignificant, remember this feeling. You are inseparable from the universe. You are made of its oldest atoms. You are sustained every moment by its physical laws. You are woven into the same fabric as every shining star and every yawning void. The gravity that holds distant galaxies in clusters is at this moment holding you to Earth and holding the atoms of your body together. The light that left a quasar billions of years ago, showing us the early universe, is the same kind of light that gently warms your skin on a sunny day. We set out seeking the cosmos, and we found ourselves. We imagined going outward to the greatest expanses, and it brought us inward to the smallest corners of our being. In truth, there is no real separation. It's all one continuous reality, from the quantum foam to the cosmic web. As above, so below, the ancient saying goes. The macrocosm reflects the microcosm. Here, at the end of our journey, sit for a moment in that understanding. Feel the quiet awe inside you. You have journeyed from a breath to the edge of time and space and back again. Let a sense of belonging and peace settle in your heart. The cosmos is vast beyond words, and it is violent and beautiful and mysterious. But it is also home. In all its enormity, it has nurtured the pathways for particles to become people who can love and dream. You are a product of this universe, as dear to it as a child to a parent, made of its substance, playing your part in its story. Above you, the stars will continue to wheel in the night sky, distant suns on their own journeys. The earth will spin, bringing dawn and dusk. Generations of humans will be born, look with wonder at the stars, and eventually return to the universe, the substance that was on loan to them for life. Perhaps one day, humans or our descendants will travel to some of those distant stars for real, extending life's reach across the galaxy. But no matter how far we go, we'll only find more of ourselves, because we are the universe exploring itself. Take one more deep breath. Inhale deeply and exhale. Feel the solidity of the ground, the pull of gravity anchoring you, the air filling your lungs with oxygen that trees made from sunlight, the quiet beating of a heart that echoes the first drumbeats of matter so long ago. When you're ready, gently return your focus fully to the here and now. Though our narrated journey is ending, the real journey, your life, on this earth, under these stars, continues. Carry this feeling of cosmic unity with you. In moments of stress or pettiness, recall how precious and unlikely it is to be here at all, a self-aware part of an ancient, magnificent universe. Let it give you perspective and solace. Above all, remember that awe you feel, that quiet, humbling sense of the sublime. The cosmos is vast beyond comprehension, and you are an infinitesimal speck, yet you are also a cosmic miracle, a part of all of this. You belong in this story. The hydrogen in your body, the stardust in your bones, the spark of thought in your mind, all of it is the universe, and it all belongs. In the grand, expanding vastness, in the still center of your own heart, feel the connection. Feel the kinship with everything that is. The cosmos is not cold and alien. It is inextricably linked to you. You are a child of the stars, an heir to the galaxies, and a partner to the universe's endless change. In this union of inner and outer, in this melding of self and all, there is a profound peace. You are home.